A cold visitor crosses the inner dark, its halo swelling, its path unbound by our Sunday Mars hangs ahead like a silent witness. Then the corridor narrows, the object slips behind the solar glare where most of our eyes cannot follow. Far beyond, Jupiter waits like a judge at the end of the hall. The timing feels too neat, the chemistry too odd, and the questions too loud to ignore. Stay with this mystery, because the simplest explanation might be the strangest of all. Imagine learning that planets do not only grow, they are planted. For decades we argued about the clock that builds giants, how to assemble a core fast enough before the gas around a young star evaporates. Now an interstellar wanderer appears, not a bound comet from our own deep freeze, but a traveller on a hyperbolic path, a geometry that says it came from another system. Astronomers call it 3I Atlas. Its course threads a sequence of encounters that reads like a script. A near pass of Mars, a perihelion draped behind the Sun from Earth's point of view, a later approach to Jupiter that promises the clean arithmetic of gravity and the cruel interrogation of radiation. No one has to invent drama here, the sky already arranged it. From the first spectra we learn that its breath is lopsided. Carbon dioxide lines flare bright while water lingers as a supporting character. Even farther from the Sun, fragments of water chemistry appear early, as if the interior responds to modest warmth with unexpected eagerness. The coma shows a sun-facing glow that teases the eye, until sharper images reveal a dust fan directed toward the light and a faint tail pointing away. Polarization measurements whisper that the dust is not like what we often see at home. Size limits from careful imaging say the nucleus is modest, a few kilometers scale rather than a city-swallowing slab. Each detail by itself is curious. Together they sketch the outline of a puzzle that is worth a long look. Known meets unknown, right away. Known, a hyperbolic trajectory marks an interstellar origin, so we can study material that was shaped in another stellar nursery. Known, solar heating can drive a sunward plume and an anti-solar tail without any need for exotic engines. Unknown, why so much carbon dioxide compared to water, and why such early activity far from intense sunlight. Unknown, whether unusual polarization hints at grains processed by long interstellar travel, or at something we have not yet modeled. The paradox sharpens. The chemistry points to formation in colder places than our familiar comet zones. The itinerary tempts stories about design, and yet the motion so far looks like the honest work of gravity and sublimation. One possibility is that this is a natural comet from a different kind of freezer, a place where carbon dioxide condensed more readily than water. A competing view suggests that the object might act as a ready-made core, a seed that young disks could capture to jumpstart planetary growth. It remains uncertain whether any pattern in the timing is more than our human eye searching for intention in a small sample. Evidence is limited, but one inference is that early discovery has given us a rare chance to plan a clean sequence of observations, from Mars vantage, through the sun-blocked interval, to the return of clear lines of sight, and finally to the sharp tests near Jupiter. A minority view holds that advanced technology could hide beneath natural-looking behavior, though such claims must clear the highest bar. We will handle the story with a rule that will not bend. Facts first, speculation labeled, and no extraordinary claim without extraordinary proof. We will test 3 roads, side by side. Natural and unusual, a seed that fits the needs of planetary theory without any whisper of machines, or an artifact that wears a comet mask. The tension will not come from shouting aliens. It will come from the way the data chips at our certainty while refusing to draw a quick conclusion. Each window in the calendar is not a twist for entertainment. Each window is a chance to tighten or relax the case. This is the promise at the top of the journey. We will keep the thrill of the unknown, but we will not betray the known. As images sharpen and spectra thicken with lines, as motion and light curves stack into patterns, we will ask the same question again and again. What would it take to change your mind? And when we reach our first observational milestone, the Mars passage that opens the trial, we will be ready to measure, to doubt, and to wonder in equal measure. Set the table cleanly, then light 3 candles. First, the ordinary that refuses to stay ordinary, a natural comet with chemistry and optics that sit at the edge of our experience. Second, an engineered traveler, a device that learned to dress like ice and dust and to move only when sunlight could be blamed. Third, a living seed, not in the fairy tale sense, but as a carrier of instructions, materials, or dormant hitchhikers that awaken only when the temperature and the light are right. These are not equal claims. They begin with unequal burdens and unequal histories, but they will share the same yardstick: observation, repeatability, and the discipline to let data surprise us. Start with the natural path, because nature has earned the first look. We have seen comets that break rules one by one, then later teach us that the rules were too simple. One possibility is that 3I Atlas formed in a region with a colder thermal history than our familiar comet belts, so carbon dioxide settled early and in abundance. A competing view suggests surface processing during a long interstellar journey could have enriched the outer layers in carbon dioxide relative to water ice. It remains uncertain whether early water signatures at large heliocentric distance reflect porosity, cracks that reach subsurface pockets, or a nucleus that is better at absorbing faint sunlight than our models expect. The forward glow that first raised eyebrows now sits comfortably inside asymmetric, outgassing, and dust physics. Polarization behavior still looks odd, which is an invitation to study grain size and structure rather than an excuse to declare technology. The artifact road is not forbidden, it is simply steep. Evidence is limited, but one inference is that a true device would leave fingerprints that are hard to wash away, non-gravitational acceleration that holds direction while sunlight and rotation try to smear it. Light curves that step through values as if obeying a schedule, not a thermal cycle. Narrow emissions that look like engineered lines rather than molecular bands. So far, we do not see these. The trajectory feels tidy, yes, but small samples and after-the-fact probability games can make tidy shapes out of noise. A minority view holds that concealment is the point, that a probe would avoid the obvious and only reveal itself when the geometry is worst for us. That claim can always be made. The antidote is patience and a checklist that does not move the goalposts. The living seed story asks us to define alive with more care than usual. Life in ice might mean microbes that sleep through millions of years and wake for brief seasons when passing stars warm the crust. Life as technology could mean materials that repair themselves, that alter porosity and jetting to maintain structural integrity, that react to heat with behavior that looks like cunning but springs from design. The softer sense of alive might mean a kit that carries the blueprints for rapid planetary growth, a ready-made core that, if captured by a young disk, leaps ahead of the clock that defeats smaller grains. This path does not need biology or intention. It only needs gravity, drag, and time. The key is to stop the three stories from bleeding into one another. If we claim alive in the literal sense, we must ask for metabolic byproducts and isotopic ratios that are very hard to fake with non-living chemistry. If we claim living technology, we must ask for control patterns, not merely curiosity. Known meets unknown again and again across these roads. Known, the object is interstellar by geometry. Known, natural physics explains large parts of what we see, from the sunward dust fan to the faint anti-solar tail. Unknown, which formation environment best matches the carbon dioxide-rich signature. Unknown, whether the dust has been processed by years in interstellar radiation fields to yield the strong negative polarization branch that observers are measuring. Unknown, whether the calendar of encounters will produce a pattern that breaks in favor of one explanation when better vantage points arrive. So, we will proceed like this. Each new observation goes on a whiteboard with 3 columns: natural comet, seed core without technology, artifact, or living technology. Each entry must include what would falsify it. The rules are simple and not negotiable. No single anomaly wins. Multiple independent lines must converge. No retreat into unfalsifiable comfort when data fail to cooperate. If the object keeps acting like a comet, that will be the story, and it will still be a good one. If it behaves like a seed that matches emerging theory for quick giant planet formation, that will be a beautiful answer that requires no extra drama. If it ever crosses the line into engineered signatures, we will not need metaphors. The sky will speak for itself. This is how we will keep tension honest. We let each road promise something, then demand that it deliver. And when the calendar flips to our first real test near Mars, we will be ready to see which candle burns brighter and which one gutters in the wind. Begin with the path itself. An interstellar object does not loop the Sunday. It arrives fast, it bends, it leaves. The curve is not a closed oval but an open sweep. Astronomers describe this with a simple test. If the eccentricity is greater than 1, the path is hyperbolic, and the Sun does not own the traveller. That single number unlocks the rest of the story. It explains the hurry, the brief observation windows, and the temptation to fill the gaps with guesswork. Speed is the gift and the curse. We get a clean experiment in celestial mechanics, and we get very little time to ask our questions. Imagine you stand beside a highway. A motorcycle roars past. You smell the exhaust only after it is gone. That is how many interstellar encounters have felt. We notice the wake, not the rider. With 3i Atlas, the timing is kinder. Early discovery means we can arrange our instruments like a relay team. Near Mars, then behind the Sun, then the post-perihelion window, then the passage by Jupiter. Even so, geometry rules us. Phase angle matters. The object brightens differently as the Sun-object observer angle changes. Tail structures appear or vanish with a small shift in perspective. Polarization signals deepen or flatten because the scattering geometry changes with every day. What looks like a personality can be a trick of viewpoint. There is another constraint, sharp but invisible. Precision astrometry is the quiet heartbeat of this investigation. Each night, the measured position lands on a grid. Fit those points with gravity alone and you get a clean path. Subtract the expected motion from the observed motion, and you get residuals. Residuals are poetry for dynamicists. If they whisper in one direction for many days, you begin to suspect a real non-gravitational push. Sublimation can do this. Natural jets act like tiny thrusters and can move a nucleus in measurable ways. Artificial propulsion would need to stand above that background. It would need persistence and directionality that disobey thermal logic. So far, the curve behaves the way a comet would behave, with the caveat that precision improves with time and that small signals hide in early noise. Selection effects shape our confidence. We are barely beginning to see these visitors in a more systematic way. The first was quiet and dry. The second looked like a familiar comet. The third is chemically odd, yet dynamically standard. 3 points do not anchor a population. A handful of events can make any pattern look improbable. After the fact, probability is a slippery friend. You can take any path and compute a low chance for that exact geometry, then forget that there were countless other specific paths that would have looked special to someone. The correct question is different. Given a wide distribution of incoming angles, how many visitors would appear near the ecliptic by chance, and how often would their waypoints line up with planets within a few months? We need a large census to answer that well. For now, restraint is our air. Hyperbolic speed compresses opportunity. Exposure times grow touchy as the object rushes by. Tracking rates climb, and small errors smear the light. Faint ion tails fade into background glare if the angle is wrong. Coma morphology can look asymmetric when rotation and viewing geometry mix in unfriendly ways. This is why the Mars window matters. A new vantage means new errors, not old ones recycled. The sun-blocked interval is not emptiness, it is a challenge to the fleet of inner system instruments, coronagraphs that can peel back some of the glare, heliophysics probes that do not share Earth's blind spot. The Jupiter leg is another world, a chance to squeeze the trajectory with the weight of a giant and to watch for even smaller residuals. Gravity turns the sky into a meter stick. Our through line remains simple. Let motion and light tell one story together, and do not let either outrun the other. When we speak of non-gravitational acceleration, we need to respect scale. Sublimation thrusts are measured in tiny fractions of meters per second squared. Over weeks they add up. They also follow the sun. They wax and wane with rotation. They echo the map of vents on the surface. Engineered control would have a different signature. It would hold a heading that does not care about local noon. It might step in clean increments in a way that a heat-driven jet cannot match. It might fade when concealment is needed, and return when geometry hides it from most lines of sight. These are testable ideas. There are also claims that can go quiet when the data stay stubbornly natural. So, geometry is not the villain of our mystery. It is the grammar that lets us say what is interstellar and what is not. The open curve, the fast approach, the tight windows, the slow refinement of residuals, the need to fit many small pieces instead of one grand clue. Each element narrows the room for fantasy and leaves a clear lane for imagination that stays honest. With that in mind, we turn from the highway to the timetable, because the neat sequence of Mars, perihelion, and Jupiter deserves its own examination. Lay out the appointments on a clean timeline, then ask why they sit so neatly. The first appointment sits near Mars, close enough that orbiters can watch without the blur of Earth air. Weeks later, the object skims past perihelion, but from Earth the Sun is a curtain that hides the stage. After that, the geometry improves and our most sensitive spectrographs regain their view. Months later, Jupiter waits at the far end, a massive audience with a talent for pulling secrets out of passing bodies. Seen as a whole, the sequence reads like a script written for maximum suspense, close reconnaissance, sudden blackout, return of visibility, finally a final exam beside a planet that bends paths and shakes comas. Patterns make us human. We see a rhythm and we wonder who is conducting. Begin with the Mars window. Orbiters that have stared at rust and ice for years can suddenly turn outward. They carry cameras that cut through the thin Martian sky, and spectrometers that catch lines erased by our thick air. They can watch for hours without sunrise to sunset, interruptions that haunt Earth-based runs. The object does, not come dangerously close to the planet, yet close enough that jet geometry and color can be mapped across rotations. If sunlight alone drives activity, the pattern will dance with local noon and with the spin of the nucleus. If some other logic runs the schedule, the pattern may hold when the sun angle swings. This is a clean test, and it arrives early, which is a gift few interstellar visitors have given us in the past. Then comes the bright wall of the Sunday. From Earth, perihelion becomes a rumor, told through heliophysics monitors and coronagraphs. This is not nothing. Specialized instruments can peel back glare and catch a faint traveler as it threads coronal streamers. Inner system probes see angles that ground observatories cannot. High heating should lift more volatiles, change the balance of carbon dioxide and water, and stir complex organics if they are present. If anything unusual hides at low activity, perihelion is where it would have to reveal itself. Concentrated heat does not respect camouflage. Yet, if nothing extraordinary appears, that is also a loud answer. A natural comet with odd chemistry will simply act like a comet under a stronger lamp. After the sun comes the return. Geometry sweetens in December. Telescopes that slept through the blackout wake with hunger. Infrared spectrographs pick at faint lines that were invisible before. Optical images compare coma structures before and after the heat. Ratios can be tested again. If carbon dioxide dominance fades or persists, that tells us something about layering and thermal skin depths. If hydroxyl emission zones expand or retreat, that tells us something about porosity and internal reservoirs. A post-perihelion comparison is the closest thing to a controlled experiment that celestial mechanics allows. The same object, similar distance ranges, different thermal history. Finally, the path turns near Jupiter. This is not a close shave in cinematic terms, yet it is close enough for precise tracking to squeeze the trajectory. Gravity in that neighborhood is a scalpel. Small deviations that hid in earlier noise can become visible when measured against the predicted bend. Radiation belts in that region batter coma grains and charge the environment. If any artificial system were sensitive to high-energy particles, this is where it might twitch. If the nucleus has odd mass distribution, the way the coma reforms beyond the encounter can hint at internal structure. The price of the Jovian exam is patience, but the reward is clarity about motion that earlier windows could not deliver. Now ask the hard question. Does this elegant itinerary prove anything about intention? The truthful answer is more modest. The sequence creates tempting theatre because our instruments are where they are and because our minds are wired for stories about design. Selection bias is an artist that works without credit. We remember clean alignments and forget near misses. We compute low odds for a path only after we have seen it, and we ignore the countless other specific paths that would also have felt unlikely. The correct habit is to treat the calendar as opportunity, not as evidence. Opportunity still matters. A planned relay of vantage points increases the odds that weak signatures rise above confusion. Mars supplies high-resolution morphology and spectra freed from Earth air. Perihelion offers a stress test under maximum heat, even if the view is indirect. The December window lets us check how chemistry evolves in a cooling coma. Jupiter gives us a precision ruler for dynamics. If the object is natural, these beats will map an unusual yet coherent story. If it is a seed ready for capture in other systems, the chemical and physical profile should match that role. If anything engineered hides beneath frost, at least one of these phases is likely to betray it. The through line holds steady. The dates are not drama, they are diagnostics arranged by geometry, and they reward patience over spectacle. So the clockwork is real only in the sense that celestial mechanics writes good schedules. We will use the schedule to push on claims that are easy to say and hard to sustain. The next step is to leave the calendar for the lab bench, to hold the spectra and the images to the light, and to ask why the chemistry is so strange and what that says about where this traveler was born. Begin with breath. A comet breathes when sunlight reaches its skin. Ice warms, molecules escape, sunlight splits them, and telescopes catch the fragments as lines across a spectrum. Most comets from our backyard breathe water first and loudest, with carbon dioxide and carbon monoxide joining as the heat deepens. This traveler does something different. Carbon dioxide stands up early and speaks with a stronger voice than water. Even farther from the sun than usual, we see signatures that belong to water chemistry appear before the heat should have woken them in force. The pattern is not an error made by one instrument on one night. Multiple readings across facilities point the same way. That is the first truth that demands a new frame. There is a simple place to look for answers. Chemistry remembers its birthplace. In colder regions of a disk, different ices settle into solids at different distances from the star. The line where water freezes out is not the same as the line for carbon dioxide. One possibility is that 3I Atlas formed in an environment colder than our usual comet nurseries, so carbon dioxide condensed in abundance relative to water. A competing view suggests that long exposure to interstellar radiation altered the surface, leaving a crust that heats in a way that favors carbon dioxide release. It remains uncertain whether microfractures allow deep reservoirs to vent earlier than expected, or whether the grains themselves have textures that change the balance between absorbed energy and escaping gas. The early whisper of water is a second clue. Telescopes seldom see pure water in these distances. They see a daughter product known as hydroxyl, forged when sunlight breaks water into pieces. The detection of hydroxyl at large distances hints at a porous interior that responds to gentle warmth and at channels that carry vapors to the surface with ease. It also hints at layered structure. Perhaps a skin rich in carbon dioxide sits above deeper pockets where water ice hides, so that a small rise in temperature can draw a narrow plume that registers in sensitive spectra, even while the coma looks carbon dioxide heavy overall. None of this requires exotic engineering, yet all of it challenges simple textbook pictures of a dirty snowball that waits for strong heat before it wakes. Light, as always, adds a twist. Early images suggested a glow that favored the sunward side. For a moment it looked like a cheat, as if light fell on a polished flank. Sharper data turned that drama into physics. A fan of dust aimed toward the sun, a faint tail in the opposite direction, and an appearance shaped by rotation and by the geometry of our view. That part slides easily into natural models. The puzzle that refuses to slide is polarization. When sunlight scatters off dust, the electric field takes on a preferred orientation, and that preference shifts with the angle between sun, dust, and observer. Many solar system comets land on familiar curves. This one traces a deeper and wider negative branch than most. The usual interpretation points to grains that are more porous, or to size distributions that are tilted, or to compositions tuned by long time in harsh space. That is not a verdict. It is a map of possibilities. A nucleus that is small by planetary standards can still carry a library of chemistry. Size constraints from careful imaging place the body in a modest kilometer class. That fact matters because it limits how much heat can build inside and how the surface cycles through day and night. A small body loses heat fast, which can preserve sharp boundaries between layers. A small body also drifts into complex outgassing behavior as rotation exposes vents to light and then hides them. In short, the chemistry we see may be a window into a stratified interior that formed in a cold cradle, then rode for ages between stars while radiation and dust impacts carved its skin into a selective filter. Known meets unknown here with a clean seam. Known, spectra show unusually strong carbon dioxide relative to water. Known, hydroxyl appears surprisingly early. Known, polarization behavior suggests dust that is different from most local comets. Unknown, the exact combination of birth environment, travel history, and surface processing that yields this profile. Unknown, whether organics of higher complexity sit below our current detection limits and will emerge after perihelion. Unknown, whether isotopic ratios will place the object in a distinct branch of galactic chemical history when better measurements arrive. Evidence is limited, but one inference is that a carbon dioxide-rich skin will respond strongly during the intense heating near perihelion. If that happens, we should see ratios evolve as deeper layers take their turn to vent. A minority view holds that a designer could prepare such layering to mimic natural responses while hiding a different purpose. That claim stalls without a decisive signature. Natural processes already account for the main features of the data. The responsible path is to turn chemistry into predictions that can fail. If water lines strengthen relative to carbon dioxide as the object warms, that supports layering in a natural interior. If complex organics appear in patterns that match thermal models rather than arbitrary schedules, that supports the same. If narrow lines appear that do not look like known molecules, then the story changes at once. We do not need every number today. What we need is discipline. Before Mars, we write down what chemistry should do if sunlight is the only driver. During the hidden days around the sun, we watch through the instruments that can still see. In December, we compare before and after with a cold eye. For now, the strange breath of this traveler reads like a postcard from a colder nursery. That postcard invites us to test a larger idea, that some visitors are not only comets, they are seeds, and their odd chemistry is exactly what a young disk would love. That is where we go next. Light can be a prankster. Point a telescope, and the sun makes a mask out of dust. Early frames of the visitor showed a bright swell on the sunward side that felt like a spotlight aimed into our eyes. For a moment it was easy to imagine a polished hull or a deliberate reflector. Then sharper images arrived. The illusion unraveled into a sun-facing fan of dust driven by heat, plus a faint anti-solar tail that stretched away like a whisper. Rotation and viewing angle finished the trick. As the nucleus turned, warm regions vented, particles burst outward, and sunlight lit the spray in a way that imitated design. What looked like intention became thermodynamics with good stage lighting. The same images nurtured a slower puzzle, polarization. Sunlight scatters off grains and the electric field becomes preferentially aligned. Measure that alignment at many angles, and you get a curve that is as distinctive as a fingerprint. Most comets in our neighborhood produce a familiar pattern. A shallow negative branch at small phase angles, then a rise into positive territory as the scattering geometry changes. This object goes deeper and holds the negative branch longer. The curve suggests grains that are more porous or more irregular than usual. It also hints at size distributions that lean toward a particular range. A single measurement might be a fluke. A season of measurement starts to look like character. Here the data ask for unusual dust, not for a hidden lamp. Known meets unknown with a steady rhythm. Known, a sunward fan plus a faint anti-solar tail fits classic outgassing physics. Known, polarization curves that deviate from the local norm are possible when grains are processed by long years in interstellar radiation fields. Unknown, which combination of porosity, composition, and grain size actually lives in the coma today. Unknown, whether the curve will evolve after stronger heating at perihelion shakes new material from deeper layers. Unknown, whether any subtle jet geometry in the Mars window will show time patterns that point to surface maps or to something with its own schedule. There is an art to not overreading light. Coma brightness can surge when many small grains launch at once, yet a slow drizzle of larger grains can carry more mass while looking dimmer to our eyes. Forward scattering near certain phase angles can make the sunward side look enchanted. Small changes in rotation state can reshape the apparent fan from night to night, and a slight change in the observer sun angle can flip the emphasis between the fan and the tail. The cure for such mischief is cadence. Watch often. Watch from more than one vantage when possible. Fold the light curves on candidate rotation periods and see whether the peaks keep time with thermal logic. This is why the Mars pass matters. Cameras in orbit there can sample the plume structure across many consecutive rotations without Earth, air, or day-night gaps. If the brightness choreography obeys sunlight, we know where we stand. If it does not, the checklist for technology earns a new tick. Polarization will keep speaking in quieter tones. A deeper negative branch can mean fluffier aggregates that pack less efficiently. It can mean coatings that change the refractive index in ways that bias scattered light. It can also record a history lesson. Grains that spent ages in the harsh between stars environment can be etched and cracked, which alters how they polarize light long after the parent nucleus begins to vent. That story is natural and testable. If the curve shifts after perihelion as fresh material joins the flow, then the dust is layered in both structure and history. If the curve holds even as the coma composition changes, then the skin and the interior may share a common origin that does not care about our distance to the Sunday. Our through line remains simple. Let motion and light tell one story together, and do not let either outrun the other. There is a practical limit to what the glow can confess. At some point we must ask about the object that makes the glow, the gritty heart that rotation exposes to sunlight. Images can only peel the coma so far before the core becomes a blur. That is where careful modeling and high-resolution data work together. Subtract the cometary haze by fitting its profile, leave a point that is the best honest estimate for the nucleus, and compare it to instrument response models to bracket size. Early efforts put the diameter in a modest kilometer class. Not a slab that could hide a city, not a pebble that tricks us with a giant cloud. A compact body with enough surface to host multiple vents and enough gravity to keep a loose grip on its shed. Size matters because it governs what heat can do inside. A small nucleus cycles quickly. Dayside warms, nightside chills, and the temperature wave does not sink deeply before the next sunrise. That preserves sharp layers if the object formed with stratified ices. It also sets the rhythm for jets that switch on and off with the march of the Terminator. If the nucleus were very large, we would expect deeper thermal storage and a slower response. The current bounds point to a nimble engine rather than a massive oven. That leans the mystery toward natural complexity and away from grand contraptions that need scale. Light misled us for a moment, then taught us a more interesting lesson. The fan is real and natural. The polarization is real and unusual. The size looks modest, which narrows the menu of possible interiors. The next honest question is simple. How big is the heart? And what does that size do to our expectations for chemistry, for jetting, and for every story that depends on secret rooms inside an interstellar stone? Strip the glow, and you reach the part that decides many arguments. The solid heart. A cometary coma can posture and disguise, but the nucleus sets the limits for every performance. If the body is large, heat can burrow and linger, layers soften, and long tunnels of vapor can form under insulating crusts. If the body is small, sunlight writes in quick strokes, surfaces flash and cool, and internal secrets remain locked behind thin walls. The best current bounds place this nucleus in a modest kilometer class. That single constraint trims whole branches from our speculation tree and sharpens the ones that remain. Think about how heat moves in a small world. Day arrives and the temperature climbs, but the warmth does not travel far before the night catches it. The thermal skin depth stays shallow. This preserves sharp chemical layers if the object was born with stratified ices. It also favors patchy activity. Vents that face the sun switch on, vents that rotate away switch off, and the cycle repeats with a regular beat. A small nucleus encourages a mosaic of geysers rather than a uniform exhale. That maps cleanly to the sunward fan and faint anti-solar tail that images have revealed. It also explains why early water signatures can appear at larger distances than expected if thin crusts crack along stress lines at local dawn. Size restrains dreams of grand machinery. A few kilometers of rock and ice leave little room for cavernous bays or for heat engines that must remain stable across ages. A compact body can certainly host complex microstructures. Pores can interconnect, grains can sinter into delicate foam, volatile pockets can sit just below the surface. Those details matter. They decide which molecules leave first and which wait for deeper heat. But they do not easily accommodate giant reservoirs of fuel that could mimic sustained thrust, unrelated to sunlight. If someone wanted to hide propulsion inside a cometary costume, a slightly larger stage would be more forgiving. The current bounds do not make an artifact impossible. They make an elaborate disguise less convenient. Grain by grain, a small nucleus tells a second story as it sheds. Gravity is weak at this scale. Particles liberated by sublimation do not need much help to escape. That means the coma can be seeded with fragile aggregates that would be crushed closer to a heavier body. Polarization data that favor fluffy grains and a deep negative branch fit this regime well. The nucleus is just large enough to host many vents, and just small enough to let exotic grains drift free without frequent collisions that grind them into simpler shapes. The dust fingerprint therefore reads like a biography of gentle liftoffs and careful escapes rather than of violent excavation. Known meets unknown at the core. Known, high-resolution imaging, and profile fitting place the nucleus in a low-kilometer range rather than a massive slab. Known, small bodies lose heat quickly, which preserves stratigraphy and explains intermittent jetting that tracks rotation. Known, weak gravity allows soft aggregates to survive the trip from surface to space, which is consistent with the unusual polarization curve. Unknown, the exact shape of the nucleus and the distribution of active areas across its surface. Unknown, whether the spin state is simple or whether subtle torques from jets are nudging the axis into precession. Unknown, whether buried layers hold richer organic chemistry that will vent only after the perihelion stress test. Evidence is limited, but one inference is that size will work as a quiet arbiter in the months ahead. If the nucleus remains within the current bounds after more refined imaging and occultation opportunities, then any claim of sustained non-gravitational NU acceleration must thread a narrow needle. Natural jets can push. They will push in patterns that echo sun, angle, and spin. Artificial thrust would need to hold a direction that ignores local noon and does not crumble under thermal cycles. The smaller the body, the harder it becomes to hide such a pattern within sublimation noise without leaving telltale steps in the residuals. There is also a clue in how the coma recovers from changes in heating. A small nucleus reacts quickly when the insulation ramps up near perihelion and again when it declines. Ratios of carbon dioxide to water should evolve on timescales that match thermal diffusion in a thin skin. If the chemistry refuses to budge, despite strong forcing, that raises new questions about surface processing or about sources of gas that are not linked to simple sunlight. Post-perihelion spectra will probe this directly. We will be able to ask whether a deeper vein of water awakened or whether the carbon dioxide skin continues to dominate in defiance of thermal expectation. A compact heart does not diminish the wonder of an interstellar traveler. It concentrates it. We are not watching a ship of cities. We are studying a rough stone that carries the memory of a colder nursery and the scars of long years between stars. Its limits help us tell honest stories. It can be a natural comet with exceptional chemistry. It can be a ready-made core that once captured would grow quickly inside a young disk. It can even be an engineered scout if a very high bar is cleared. What it cannot be, on the evidence so far, is a stage for endless miracles that never share a mechanism. Size keeps us honest. The next question follows naturally. If alive inside is to mean anything beyond metaphor, what forms could that life take within a world this small, this cold, and this constrained? The answer requires careful definitions and even more careful tests, which is where we turn our attention now. Alive is a word that glows until you point a microscope at it. In a small, cold, porous world, Alive could mean three different things, each with its own hard requirements. The first is literal biology, microbes that endure deep freeze and radiation for spans longer than civilizations. The second is living technology, materials that behave as if alive because they repair themselves and adapt their porosity and jetting in response to heat and stress. The third is a looser idea, a seed kit that carries the chemistry and architecture needed for rapid planetary growth, not life in cells, but life as potential that waits for a disk to capture it. If we do not define these carefully, we will blur tests and reward the loudest story rather than the truest one. Begin with biology, because it is the most charged. Earth has taught us humility. Tardigrades survive vacuum and extremes of temperature. Deinococcus resists radiation that would unravel other genomes. Microbes have slept in Antarctic ice and woken after long winters. One possibility is that similar hardiness could exist in alien strains, tucked within meters of shielding ice where cosmic rays lose their bite. It remains uncertain whether interstellar time is too long for repair to keep up with damage, since metabolism would be nearly frozen and chemical fixes would crawl. A small nucleus helps a little and hurts a little. It helps by keeping thermal waves shallow, so long-lived habitats can avoid disruptive melt cycles. It hurts because activity is patchy and violent on short timescales, which can desiccate or eject protective layers without warning. A competing view suggests that alive could be a property of engineered matter. Living technology is a phrase for materials that change in response to conditions, not with instincts, but with instructions embedded in structure. Imagine a lattice that tightens when warmed, closing cracks that would otherwise grow. Imagine pores that shift size to keep gas flow within a safe range for the host rock. Imagine vent orifices that self-adjust to maintain a luminous fan that looks random to us, but is actually the sum of many simple rules. Evidence is limited, but one inference is that this category would leave signals in timing. Control leaves a fingerprint, even when the designer hides it. Patterns could repeat out of step with solar forcing. Jets could hold a direction through nightside intervals when a natural vent would rest. Residuals in the orbit fit could show gentle steps that align with design choices rather than with local noon. The softer seed kit idea needs less magic. A ready-made core that carries volatile rich layers and a dust recipe that encourages fast aggregation is alive only as an opportunity. It waits for gas drag in a young disk to slow it down, then it becomes the center of a growing world. Chemistry matters here more than metabolism. A skin rich in carbon dioxide can keep outgassing across a wider range of distances, which increases effective cross-section for capturing solids. Fluffy grains lift easily from a small nucleus, then they collide and stick more readily than compact grains. A stratified interior can feed waves of material into a disk, first water, then other volatiles, then organics that survived the long crossing. This is a picture with clear tests and no need for intention. It is also a picture that fits the current hints from spectra and polarization, though it still needs stronger evidence from the perihelion interval and the December window. Known meets unknown with caution. Known, biology on Earth can endure terrible conditions for impressive periods, but not forever, and not without at least occasional repair. Known, engineered adaptive materials exist in early forms in our laboratories, which makes the concept of living technology plausible for a civilization with time to spare. Known, a seed kit matches an emerging framework in planetary science that seeks faster routes to giant cores. Unknown, whether any metabolic byproducts can be detected in the outgassing of our visitor. Unknown, whether timing patterns in jets will betray control rather than climate. Unknown, whether isotopic ratios will point to formation conditions that favor the seed story over a more mundane origin. One possibility is that biology within the nucleus would announce itself through complex organics and through isotopic ratios that diverge from abiotic pathways. A minority view holds that biology could hide completely behind abiotic chemistry under these conditions. That view is hard to falsify and must be treated with suspicion. A competing view suggests that living technology would be humble, not grand, content to keep a structure intact, not to perform miracles. That would still leave signatures in fine timing and in subtle accelerations. It remains uncertain whether our current instruments can chase such delicate hints through the glare and the noise. We can build a simple ladder of proof. First rung, do we see organics and isotopes that stretch natural chemistry beyond comfort? Second rung, do we see time patterns that contradict thermal logic? Third rung, do we measure sustained accelerations that refuse to line up with sunlight and spin? If we stall on the first rung, biology fades. If we climb the first but fail on the second and third, the seed kit becomes the most honest kind of alive. If we climb them all, then our story changes from wonder to contact, and every other part of the script must be rewritten. For now, definitions will protect us from wishful thinking. Alive can mean cells, circuits, or capacity. Our job is to keep those meanings separate while the sky offers us chances to test them. In the next part, we will take the living technology thread and pull it harder to ask what an engineered material would actually do under sunlight, and how often nature can imitate the same trick. Begin with a material rather than a machine. Imagine a body whose substance contains rules. Heat arrives, pause, tighten or open, cracks knit, vents resize to keep flows within safe limits. No circuits on a board, no obvious exhaust, only matter shaped to react with purpose. Engineers on Earth already coax metals to remember shapes and polymers to self-heal. Scale those ideas across centuries and across a civilization that has time to fail and try again. The result could be a cometary disguise that does not carry a hidden engine. The disguise is the engine. In such a thought experiment, the object behaves like stone and snow, yet every grain carries an instruction that serves a long mission. What would such matter do under sunlight? One possibility is that vent throats would resize to keep jets in a band that is optimal for structural survival. That behavior would suppress extremes. Brightness would avoid wild peaks or collapses, and would instead step through soft plateaus as though a caretaker watched the gauges. A competing view suggests that a designer would let the exterior look messy and would place the control deeper where we cannot see. In that case, the timing pattern would still betray intent. Vents would sometimes hold direction through the local night, because the control law cares less about warmth and more about maintaining a trajectory or a rotation state. It remains uncertain whether our current cadence is fine enough to catch such quiet regularity among the natural pulses of sunlight and spin. Non-gravitational acceleration is the harshest judge of control. Natural jets push, slow, and twist according to a map that honors the Sunday. An engineered thrust pattern would need to pretend that same loyalty, or would need to be gentle enough to hide in the scatter. Evidence is limited, but one inference is that camouflage cannot win every skirmish. Over weeks, a preferred direction will accumulate in the residuals if intention is present. The signature would not be a single spike. It would be a bias that refuses to average away and that holds sign across rotation cycles and changing phase angles. We do not see such a bias yet. That confession matters. It lowers the prior for living technology without erasing the category. It also challenges advocates to define what signal would finally make them let go if it never appears. Material that behaves like life could also sculpt the dust. Porosity might be tuned to release aggregates of a favored size that drift without clumping too quickly. Coatings could set refractive properties that manage temperature by redirecting specific wavelengths deeper or back into space. Polarization curves might carry the fingerprints of such choices. A minority view holds that unusual polarization is enough to claim design. That claim does not survive contact with the laboratory. Interstellar processing can fracture and etch grains into forms that polarize light in unexpected ways. The safer path is to ask whether polarization evolves after perihelion in a manner that follows simple thermal ideas. If it does, design recedes. If it does not, then we push harder on the thought experiment and look for correlations with any small changes in trajectory. Our through line remains simple. Let motion and light tell one story together, and do not let either outrun the other. Instruments give us several handles on the idea. High-cadence imaging near Mars can clock jet directions through full rotations. If a vent keeps pointing when it should sleep, that is interesting. Light curves folded on rotation can reveal beat notes that make no thermal sense. Spectrographs in December can test whether volatile ratios change in sync with heating, or hold suspiciously steady across varying distances. Precise astrometry around the Jupiter leg can push the residual floor low enough to expose gentle control that earlier fits could not see. These are not magic bullets. They are a suite of ordinary tests that together can make extraordinary stories unnecessary. Known meets unknown with a fair handshake. Known, we have no need for. They're designed to explain the current ensemble of observations. Known, small bodies with patchy activity, produce time series that can look complex even when they are innocent. Unknown, whether longer baselines will reveal quiet persistence in directions that thermal logic does not predict. Unknown, whether narrow spectral features will appear that belong to materials rarely formed in natural settings. Unknown, whether rotation state will evolve in a way that hints at deliberate torque management rather than the familiar dance of outgassing. One possibility is that living technology would prove itself through resilience. The object would ride perihelion without dramatic fragmentation because control rules keep stress within margins. A competing view suggests that resilience also describes many natural comets that are simply lucky in their internal structure. It remains uncertain whether any failure or survival near the Sun can discriminate between design and chance. Evidence is limited, but one inference is that only a confluence of signatures will persuade. Timed jets that ignore dawn and dusk, residuals with a stable sign over many rotations, spectral surprises that act like the calling cards of exotic compounds. Without this convergence, natural explanations will continue to carry the day. The thought experiment is still worth the effort. It teaches us what to look for and how to rule out the most alluring mirages. It also keeps us honest about our appetite for intent. We like stories with makers. Space does not care about our taste. The next parts will put the artifact hypothesis on a formal stand. We will set thresholds, we will present exhibits, and we will keep the same rule. Beautiful math or eerie timing does not convict. Physics does. Begin as a courtroom, not a carnival. The claim on the table is simple to say and very hard to prove. Could this object be an engineered device that wears a comet mask? The burden of proof is not shared equally. Natural explanations have centuries of precedent and a wide library of laboratory physics behind them. Artifact claims must clear a higher bar because they ask us to overturn the default. So we set rules of evidence that protect curiosity while guarding against spectacle. First, geometry and coincidence cannot convict by themselves. Second, statistics computed after the fact are color, not core. Third, only physical signatures that cannot be reconciled with sublimation and dust physics can move the verdict. Exhibit 1 is the itinerary that feels arranged. Mars first, then a hidden perihelion, then a clean December window, then a precision pass near Jupiter. The pattern tempts a story about reconnaissance. One possibility is that a device could have optimized for our blind spots and for our strongest telescopes. A competing view suggests that we notice neat sequences precisely because they are neat, and that we forget the many visitors we never detected or the many geometries that would have looked compelling for different reasons. It remains uncertain whether the current path is rare in the true population. Evidence is limited, but one inference is that surveys with higher cadence will make tidy alignments more common and less suspicious. In the meantime, the itinerary is a gift for testing, not a clue that closes the case. Exhibit 2 is light. Early frames showed a swollen glow that favored the sunward side. Speculation rushed in. Then, better images resolved a dust fan and a faint tail. Thermodynamics under sunlight can sculpt exactly this shape. Polarization remains unusual, which keeps everyone honest. A minority view holds that odd polarization implies engineered particles. That view ignores how interstellar radiation can roughen grains and shift refractive properties in natural ways. The sober position is to watch whether the polarization curve evolves as deeper layers vent after perihelion. If the curve tracks thermal history, design fades. If the curve refuses, and to change when chemistry does, design regains a small step. Exhibit 3 is chemistry. Carbon dioxide speaks louder than water at distances where water often dominates for local comets. Hydroxyl appears early, which hints that water is present and accessible despite the cold. One possibility is a layered interior with a carbon dioxide-rich skin on top of deeper water ice. A competing view suggests surface alteration during a long interstellar journey that favors carbon dioxide release. It remains uncertain whether deeper heating near perihelion will rebalance the mix. None of these options require machines. They ask for different birthplaces and travel histories. They also produce predictions. If ratios evolve with heat as expected, the artifact claim loses oxygen. If the mix holds unnaturally steady across changing insulation, the claim earns a closer look. Exhibit 4 is motion. This is the decisive arena. Non-gravitational acceleration from natural jets does not pick a single heading and hold it with pride. It wobbles with rotation, it breathes with local noon and local night, it rises and falls with heliocentric distance. Artificial thrust would need to leave a bias that persists across many rotations and across changing phase angles. Residuals would whisper the same sign for weak. The fit would fight to explain the curve with sunlight and would fail in a way that repeats. We do not have that pattern yet. That absence is not a final verdict, because sensitivity improves as the arc length grows and as tracking near Jupiter sharpens our ruler. It is, however, a heavy fact. The default stays the default until the default cannot carry the numbers. Our through line remains simple. Let motion and light tell one story together, and do not let either outrun the other. Cross-examination matters. If advocates of the artifact hypothesis move the goalposts each time a natural explanation appears, the claim becomes unfalsifiable. That is a philosophical error, not a scientific move. A fair trial sets thresholds in advance, a narrow spectral spike that sits where no known molecule lives and that repeats across instruments would count. A sequence of brightness steps that ignore rotation and persist through geometry changes would count. A sustained residual that holds a heading unrelated to the sun would count. Without these, the case is rhetoric dressed as wonder. There is also the practical question of intent. If a device wanted to hide, why wander through a system with dozens of telescopes and a calendar of cooperative spacecraft? If a device wanted to be seen, why present behavior that looks mostly natural and requires specialists to find the anomalies? A minority view holds that the purpose is to test our attention rather than to deliver a message. That kind of narrative is hard to test and easy to enjoy, which is a warning to set it aside until physics calls it back. The verdict today is provisional. The artifact hypothesis remains an idea under trial, not a conclusion. It is worth keeping in the room because it sharpens our tests and forces clarity about what would count as proof. It is not worth elevating above natural explanations that already explain the lion's share of what we see. The calendar ahead will keep us honest. If a device hides there, it will struggle to hide from all windows. If nature alone is at work, the windows will show a coherent arc that grows more ordinary as data improve. Either way, the trial is good for us. It teaches discipline. It keeps awe and rigor at the same table. If there is a device hiding inside an honest-looking comet, it must leave a trail that nature struggles to mimic. The most persuasive clues are not cinematic. They are patterns that refuse to dissolve when you average them and test them from more than one angle. We can lay them out like a quiet checklist, not to tempt belief, but to anchor restraint. Each item is simple to state. Each item is hard to fake with sunlight and ice. Begin with motion that does not care about noon. Natural jets push in directions that drift with the rotation of the nucleus. The push changes as different surface patches warm, and it weakens as the object cools. If there is guidance, the residuals in the orbit fit should hold a preferred sign for many days. The bias should persist as the phase angle changes and as the object rotates. The magnitude might vary, but the direction should look stubborn. One possibility is that a very gentle control could still hide within the noise of sublimation. It remains uncertain whether our present precision can extract such faint discipline before the Jupiter leg sharpens the ruler. Evidence is limited, but one inference is that any bias that survives a full rotation census is strong medicine. Next is choreography that ignores the thermal drum. Fold a light curve on the rotation period, and the peaks line up with local noon for natural vents. If the pattern steps across the cycle in a way that refuses to lock to sunlight, then something else keeps time. A competing view suggests that complex topography can mimic this by shadowing or by thermal lag in certain materials. That is why cadence matters. You watch long enough to catch many rotations. You change geometry so that the shadows fall differently. If the odd timing survives those changes, the case grows interesting. If it melts away when the angle shifts, the mystery was the geometry, not a conductor hidden in stone. Consider spectral lines that act like name tags. Molecules have habits that are hard to counterfeit. They absorb and emit at specific wavelengths and at ratios that reflect temperature and density. A narrow spike that sits alone, that repeats across instruments, and that refuses to match known molecular catalogues is a direct challenge to nature. A minority view holds that rare terrestrial pollutants can masquerade as exotic lines in certain setups. The response is simple. Confirm the line with space-based spectrographs. Confirm it with ground facilities that control for contamination. Confirm it at different times so that instrumental quirks have room to betray themselves. If the spike remains, it belongs to the sky. There is a softer class of signature, but it is no less telling. Chemistry that refuses to evolve under strong heating is suspicious. A carbon dioxide-rich coma should change as deeper layers warm and vent. Ratios should drift toward water dominance, at least for a while, if stratigraphy rules the interior. If the ratios freeze in place across wide swings in insulation, then a mechanism is holding the mix steady. One possibility is a crust that self-regulates permeability in a way that prefers certain molecules. A competing view suggests that thick layers of carbon dioxide can overwhelm deeper water for longer than our intuition expects. The perihelion interval and the December window will test this directly. It remains uncertain which way the balance will tip, and that is why those dates matter. Polarization can also join the list, but with caution. Engineered grains could have optical properties designed for thermal control or for camouflage. They could produce a deep negative branch that looks unusual. Nature can do that too. Interstellar radiation and the long grind of time can turn grains into porous aggregates with odd refractive behavior. The responsible use of polarization is comparative. Watch whether the curve shifts as fresh material joins the coma after stronger heating. If the curve holds steady while the composition changes, then something beyond layering is at work. If the curve evolves in step with other signs of new material, then nature retains the lead. Our through line remains simple. Let motion and light tell one story together, and do not let either outrun the other. None of these tests win alone. Each can be faked by geometry, or by selection effects if taken in isolation. Together they behave like a cord that tightens or loosens with new data, non-gravitational residuals that keep a heading through rotation, light curves that step in a pattern that refuses to obey the Sunday, spectral spikes that do not belong to known molecules and that survive careful checks, chemical ratios that sit strangely still through a thermal storm, polarization that ignores the arrival of fresh dust. If several of these arrive at once, and if they are confirmed independently, then the story leaves the realm of nature and enters the realm of design. Known meets unknown with clear labels. Known, the object behaves like a comet in its broad strokes. Known, unusual chemistry and dust are compatible with cold birthplaces and long interstellar travel. Unknown, whether small but persistent control signals hide in the noise and will emerge when we extend the arc of observation. Unknown, whether the most sensitive spectrographs will reveal lines that our catalogues cannot place. Unknown, whether the post-perihelion evolution will cooperate with simple thermal expectations. So the checklist is not a prophecy, it is a contract. We agree to elevate our claims only when several items turn green at the same time. We agree to stand down when they do not. With that in hand, we can face the other side of the balance, the scientific guardrail that keeps discovery from collapsing into spectacle, and ask why doubt is not an enemy here, but an ally that protects the wonder we seek. Skepticism is not a wet blanket thrown over a good fire. It is the stone ring that keeps the flame from running wild. In stories about the sky, that ring matters more than ever. The artifact tale is exciting, the seed idea is beautiful, the biology whisper is irresistible. Without a guardrail, the show can slide from wonder into superstition, and the audience cannot tell the difference. So we pause and build the case for doubt as a practice, not as a mood. Doubt does not mean cynicism. Doubt means rules for when to lean forward and when to lean back, And it means the discipline to label a claim with the right level of confidence and to leave it there until the numbers move. History gives us a clear script. Pulsars arrived as sharp radio flashes that felt too tidy to be natural. Some called them beacons and smiled at the nickname. Then neutron star models matured, and the signal found its place in physics. Fast radio bursts were brighter and quicker and stranger. For a time, they floated in a sea of headlines that loved their mystery. Instrumentation grew up, and catalogues thickened, and mechanisms appeared that matched the strength and the speed. Tabby's star dimmed and flickered in a way that begged for a machine to explain it. Dust won in the end. Each time the thrill remained, but the claim changed clothes. A guardrail kept the field from wandering into a parade of untestable stories. The reason is simple. Extraordinary claims carry extraordinary costs when they fail. Public trust slides. Future announcements sound like marketing, even when they are careful. Young scientists learn the wrong lesson about how to earn attention. The guardrail exists to protect the long chase after real extraordinary events. It asks for a visible ladder of evidence that anyone can climb and check. It rewards predictions that can fail. It punishes goalposts that move. It prefers statements that grow from conservative to bold in step with data that grow from sparse to rich. It keeps spectacle in service of knowledge rather than the other way around. There is a second reason to love the guardrail. It makes discovery sweeter. If most anomalies resolve into natural explanations, then the few that do not are easier to believe. A community that says wait often is a community that can say yes once in a while and be taken seriously. That is the contract with an audience that has been disappointed before. We tell them what we know. We tell them what we think. We keep the two piles separate in plain view. We promise to change piles in public when the evidence warrants it. Trust grows. Curiosity survives. Apply this to our visitor. We can stage bold claims, but we tape down the corners with tests. We can frame the itinerary as dramatic, but we refuse to treat drama as evidence. We can marvel at polarization that stretches the usual curve, but we also show how fragile grains and long radiation processing can sharpen that negative branch without any design. We can admire a carbon dioxide-rich coma, but we ground that admiration in thermal models that predict how ratios should evolve with distance and with time. We can present a checklist for technosignatures, but we agree that none of the boxes is green until it survives many nights and more than one instrument and more than one geometry. Known meets unknown with a steady hand. Known, science advances fastest when bold ideas are allowed to breathe, then are forced to earn their keep. Known, instruments fail sometimes, and data pipelines can burp, and selection effects can fabricate patterns that do not survive replication. Unknown, which small signals in this case will survive the winter of new observations. Unknown, whether the December spectra will strengthen waterlines as thermal logic predicts. Unknown, whether the Jupiter leg will reveal residuals that stay loyal to a heading. Those questions are not a fog, they are a map. One possibility is that the public rhythm of this story feels quiet for stretches. That is not a flaw, it is how careful work sounds. A competing view suggests that audiences will drift without constant surprises. Our experience argues otherwise. People can handle suspense that is paced by honest milestones. It remains uncertain whether the most dramatic expectations will adapt to a season of sober updates. Evidence is limited, but one inference is that clarity beats volume when the terrain is this rare and the stakes are this high. A minority view holds that open speculation with thin support is harmless. The counter is that it changes baselines, and baselines are hard to reset once they slip. Our through line remains simple. Let motion and light tell one story together, and do not let either outrun the other. The guardrail is not a fence around imagination. It is a path down a mountain that many have slid from. Follow it, and you can still stop for views. Lean over the edge, and you can still feel the drop. But you move with purpose, and you arrive at the valley with more than a tale about how dizzy the cliff felt. With the ring in place, we can turn to the most creative natural idea on the table, a mechanism that could change planetary theory without calling on machines, and that turns our visitor from a prankster into a courier from colder rooms of the galaxy. Imagine a busy nursery where stars are born in clusters, gas swirls, and dust drifts like weather. In that crowd, the clock is cruel. Disks of gas and dust do not last forever. They thin and vanish within a few million years. Classic models that grow giant planet cores grain by grain struggle to beat that clock. Here is where an interstellar wanderer offers a different play. It arrives already big for its weight class, with volatile, rich layers and a surface that sheds grains eager to stick. If a young disk captures such a body, the system starts in the middle of the story rather than at the first page. This is the simple power of the seed idea. Time saved is everything. Begin with the capture. Gas drag inside a young disk can bleed energy from a passing object. The path bends, speed falls, and what was a guest becomes a resident. That effect strengthens in dense disks and in clusters where encounters are more common. One possibility is that 3I Atlas is a member of a large hidden population of such wanderers. If the galaxy is full of small bodies ejected from forming systems, then young stars are not only building worlds from local supply, they are also fishing ready-made cores from the stream. A competing view suggests that capture is rare and that most intruders fly through without losing enough speed. It remains uncertain where the true rates fall. Evidence is limited, but one inference is that larger surveys will decide this by counting visitors and by measuring their size distribution with less guesswork. Now, consider chemistry. A seed that prefers carbon dioxide at the surface can begin venting at larger stellar distances than a water-dominated body. That early breath puffs an envelope around the nucleus and increases the effective area for colliding with solids in the disk. Fluffy grains that lift easily from a small nucleus collide gently and stick rather than shatter. This creates a self-reinforcing loop. The more the seed exhales, the larger the target it presents to passing pebbles, and the faster it grows. If deeper layers are rich in water and organics, the seed can later enrich its neighborhood with the ingredients that young atmospheres like to capture. None of this requires intention. It is a graceful accident of physics and place. Known meets unknown with room to learn. Known, disks disperse quickly, which challenges slow growth. Known, capture by gas drag is a real mechanism in models of young systems. Known, our visitor shows a carbon dioxide, strong signature, and early water chemistry that fit the profile of a volatile, rich seed. Unknown, the true abundance of such bodies in interstellar space. Unknown, whether isotopic ratios in a seed like this will point to birth environments different from our local comet zones. Unknown, how often a captured seed retains enough integrity to become the core of a giant planet, rather than grinding down into a cloud of debris. We can sketch testable consequences. If seeding is common, then giant planets should be somewhat more frequent around stars born in crowded clusters where captures are easier. If seeding is real, then some exoplanet atmospheres should carry chemical fingerprints that do not match the chemistry of their host disks, because the cores were imported from other nurseries. If seeding operates, then the population of interstellar objects should include a wide spread of chemistries that trace different birthplaces. A minority view holds that all of these effects can also arise from local diversity without any need for imported cores. That is possible, and the way to separate the stories is by combining better counts of visitors with deeper chemical measurements of disks and planets. Our visitor offers a near-term test. As it warms and cools, we will learn how its layers respond. If ratios of carbon dioxide to water evolve in a way that tracks a stratified interior, then the seed picture gains support. If polarization changes as deeper dust joins the flow, then porosity and grain sizes will find a place in the map. If organics emerge in patterns that match thermal expectations, then the seed has delivered a sample of what a young disk might inhale. Each of these findings would also be compatible with a natural comet that never sees a disk. The difference is not in the data alone. It is in the way we connect that data to a wider theory of how systems grow. One possibility is that the seed hypothesis will turn out to be a partial truth. Some worlds will grow this way in dense nurseries. Others will grow slowly from local stock in quieter neighborhoods. It remains uncertain whether the seed path dominates or merely assists. Evidence is limited, but one inference is that the truth will sit in a mix that depends on environment, on stellar mass, and on the history of nearby stars that shed and swap material. That is a satisfying answer for a galaxy that enjoys variety. The planet seed idea does something generous for our story. It gives us a way to be radical without stepping outside natural law. It asks us to look at an interstellar traveler and see a courier rather than a spy. It aligns the odd chemistry with a purpose that does not need a builder. It turns capture into a creative act and time saved into a bridge between problem and solution. With that frame in mind, we can now ask the next practical question. How does capture actually work in detail, and what signatures would a captured seed carry that we can still read billions of years later? To understand capture, slow down the picture. A young star glows inside a disk of gas and dust that is thick like fog. The fog moves in circles, not too fast, not too slow, guided by gravity and pressure. An interstellar traveler cuts through this scene like a pebble thrown into a river. Gas molecules strike its surface and steal momentum. Dust grains buffet its flanks and add drag. The path tightens. The energy budget shrinks. A loop begins to form where an open arc once ruled. If the conditions are right, the loop closes and the traveler is no longer a visitor. It becomes part of the family. Gas, drag, is the first actor. The effect is strongest in dense inner regions and during passages that cross large columns of material. One possibility is that a seed enters on a path that grazes the midplane of the disk. There the density is highest, the relative velocity is not too extreme, and the braking effect has time to work. A competing view suggests that most entries are too fast or too glancing, and that the seed escapes after shedding only a little speed. It remains uncertain where the odds sit for a typical cluster. Evidence is limited, but one inference is that the chaotic gravity of many young stars can guide a seed into several near misses before one finally takes hold. Clusters amplify the chance. Hundreds of siblings form together, and their gravity sculpts the neighborhood. Close encounters swap energy. A seed can arrive with a speed that would mean escape in isolation. Then a mild tug from a neighbor star reduces that speed just enough to grant the disk a chance to finish the job. The same crowd raises the number of seeds in circulation, since young systems eject debris as they reorganize. Capture does not need to be common to matter. It only needs to be common enough to solve the clock problem for a meaningful fraction of giants. The larger the crowd, the more likely the handoff. Chemistry leaves clues to birthplaces. Disks carry snow lines, boundaries where certain molecules freeze out into solids. Water ice forms closer to the star than carbon dioxide in many conditions. If a seed formed far from its star in a region that favored carbon dioxide, its outer layers would record that choice. When captured by a new disk, that seed will breathe a pattern that does not match the local gradients. One possibility is that isotopic ratios in water and carbon compounds will diverge from the ratios that the host star would imprint on locally born material. A competing view suggests that mixing inside large disks can blur such differences until the chemical fingerprints are hard to read. It remains uncertain whether current telescopes can resolve these small offsets at the distances where exoplanets are found. Capture changes the speed of growth. A seed that measures a few kilometers across holds gravity that a pebble cannot match. It focuses passing solids into a wider target and builds mass much faster than a swarm of tiny grains would. In a thick disk that advantage compounds, a small core becomes a larger core. A larger core begins to collect gas as well as solids. A race against evaporation becomes a race that a captured body can finally win. If the seed continues to exhale volatiles while it grows, that outflow can also help it sweep up pebbles by increasing the cross-section of the surrounding cloud. This is not a plan. It is a fortunate feedback loop that natural selection in space would find and use without ever meaning to. Known meets unknown right inside this mechanism. Known, gas drag can capture intruders in simulations under realistic conditions. Known, clusters raise interaction rates that make multi-step captures possible. Known, our visitor presents a chemistry that fits a cold berth and a surface ready to vent early. Unknown, the frequency of such captures in the actual galaxy. Unknown, the lifetime of captured seeds before collisions or tides break them down. Unknown, how often a captured seed grows into a giant planet core rather than becoming part of a ring or a belt. We can imagine signatures that survive the ages. A planet built on an imported seed might show atmospheric ratios that do not match the host star metallicity trend. Its moons and rings might carry dust that polarizes light in a way that resembles interstellar processing rather than local processing. Its core might contain trace elements that point to a different nucleosynthetic neighborhood. These are subtle clues. They demand patient surveys and careful statistics. They also suggest that the story of a single traveler can feed a map of many worlds when the catalog grows. One possibility is that capture efficiency depends strongly on where and when a star is born. Dense clusters with many massive siblings may grow giants quickly with imported seeds. Quiet neighborhoods may rely on old-fashioned local growth for smaller worlds. A minority view holds that capture is so rare that it can be ignored in theory. That view will live or die by the counts delivered by new surveys of interstellar objects and by improved models of young disks. It remains uncertain which outcome will win, but the path to an answer is clear. Our through line remains simple. Let motion and light tell one story together, and do not let either outrun the other. We have traced the mechanism from foggy disks to subtle fingerprints. The next step is context. What do earlier interstellar guests teach us about diversity and caution? How do their quiet successes and loud surprises shape our expectations for the current traveler? The lesson begins with 3 visitors and 3 different ways to be strange. Line up the 3 travelers in the sky, begins to speak in contrasts. The first was quiet and angular, a dim shard that never raised a coma loud enough for waterlines. The second looked like a textbook comet, a generous tale, and a chemistry that did not try to surprise. The third arrives as a contradiction, active yet odd, with carbon dioxide taking a leading role while water lingers in the wings at distances that usually keep it backstage. With only 3 points, we cannot draw a robust curve, yet each point holds a different lesson about how to think, how to test, and how not to fall in love with a single story. Start with the first, the object that entered the language as a question mark. No roaring jets, no thick veil of water vapor, only a brightness pattern that hinted at a stretched or flattened body, and a small non-gravitational push that fueled many ideas. One possibility is that sublimation from exotic ice could have delivered a gentle shove without making a bright coma at visible wavelengths. A competing view suggests that reflective geometry and tumbling alone can mimic some of the odd light curves that sent the field into speculation. It remains uncertain where the final balance of explanation sits for that single flyby. The lesson is methodological. When activity hides, minor forces matter more, and the temptation to explain them with designs can outpace the patience required to wring every natural drop from the data. The second traveller gave the comfort of the familiar. Gas and dust rose on cue. Ratios fell within expectations for comets that grow cold far from their star. Polarization and morphology did not strain the models. If the first visitor provoked 1,000 arguments, the second delivered a teacher who repeats the lesson slowly and clearly. Evidence is limited, but one inference is that the second object proves our instruments, and pipelines can read an interstellar comet. Honestly, when it behaves like many local ones, that matters. It means that when the third visitor starts to sing in a different key, we can trust the notes. We are not hearing artifacts from new hardware or from a fad in data reduction. We are hearing a real departure in chemistry and dust. Now stand before the third, our present mystery. Early water chemistry shows up where it often does not. Carbon dioxide steals the spotlight. A sun-facing fan emerges that fooled some eyes until resolution improved, and a faint anti-solar tail follows the rules that sunlight writes. Polarization paints a deeper negative branch than many of our homegrown comets. Size estimates land in the modest kilometer class rather than the cinematic. Each of these details is not shocking on its own. Together, they turn a simple label like comet into a more layered story. One possibility is that this object was born in a colder nursery, where carbon dioxide condensed more readily than water. A competing view suggests surface processing during a long interstellar journey set up a skin that releases carbon dioxide sooner and louder, while deeper water waits for stronger heating. It remains uncertain whether post-perihelion spectra will bring water forward as models predict. That is a test within reach rather than a hope stretched thin. The three lessons speak to our habits as much as to the heavens. The first says that absence of a bright coma does not imply absence of natural ways to push a body around. The second says that sometimes a visitor is a comet that looks like a comet, and that confirmation has value beyond comfort. The third says that odd does not mean engineered, and that chemistry can carry the fingerprints of distant birthplaces we have yet to sample directly. A minority view holds that the current object must be more than natural because too many pieces feel arranged. The antidote is the pair of disciplines we have repeated since the start. Compare like with like across visitors, and separate what our eyes crave from what our instruments record. Known meets unknown in a way that can be healthy if we let it. Known, 3 visitors have delivered 3 profiles, one quiet and ambiguous, one familiar and generous, one active and unusual. Unknown, the true distribution of such profiles in a population that surveys will finally reveal. Unknown, whether our present mystery sits near the center of that distribution or out on a tail where our intuition fails. Unknown, how many other chemistries wait in the catalogue once the sky is watched often enough. Our through line remains simple. Let motion and light tell one story together, and do not let either outrun the other. A final echo from the trio is practical. Diversity is a tool. By seeing how light curves behave when gas is scarce, how spectra look when activity is rich and ordinary, and how polarization shifts when dust grains are unusual, we build a matrix that future visitors will fit into quickly. The first showed us how far geometry and residuals can drag us without help from a loud coma. The second validated our instincts and our machines. The third opens a channel between chemistry and birthplace that could fuel the seed idea without asking for machines. With those 3 lessons packed, we turn to the future. The coming census will change our baselines from anecdotes to statistics, and once that happens, the story of any single wanderer will become clearer by reflection against the many. Picture a sky that is never truly dark, not because of city glow, but because a survey paints it again and again. Every few nights, the same fields are swept, the same star patterns are measured, the same streaks are checked against a ledger that grows by the hour. This is the promise of the coming census. When you look often enough, and regularly enough, the rare becomes routine. Objects that once slipped through gaps begin to stack into a population. With that shift, the tone of our mystery changes. Instead of arguing about a single traveler with a handful of data points, we begin to compare dozens, and then hundreds. Patterns rise from the noise, and confidence stops resting on clever stories and starts resting on counts. The method is simple in spirit. You take deep images of wide fields, you repeat them with a steady cadence, and you subtract one night from the next to find what moved. Some dots slide, some smear into short trails. The software that watches these differences can propose orbits within minutes. Humans then clean the list and schedule follow-up observations before the visitors grow faint. The more nights you repeat this, the better your sensitivity becomes to faint, fast, odd objects that would have escaped in older programs. A survey designed this way does not only find interstellar bodies, it finds everything that moves. Yet within that flood is the sample we crave, unbound travelers on open curves, bearing chemistry that was cooked in other kitchens. Why does this matter to our current visitor? Because probability is unkind when the sample size is 3. A path that looks special can feel inevitable once you have seen it, and the mind draws a circle around it as if the circle had always existed. With a large census, we can ask the right questions without tricks. How often do interstellar objects arrive near the ecliptic by chance? How often do their waypoints fall near planets that we care about? How widely do the ratios of carbon dioxide to water vary? How often do polarization curves show deep negative branches? The answers will not come as poetry. They will come as histograms. Those histograms will rescue us from after-the-fact marveling. A steady census also calibrates our instruments and our instincts. When thousands of detections flow through an automated pipeline, you learn how often a camera lies, how often a cosmic ray spike masquerades as a narrow spectral line, how often subtraction artifacts fake a short trail. You also learn the real distribution of sizes and activity levels, which tightens the bounds for any single case. If our present traveler sits in the bulk of a distribution, the temptation to crown it as unique will fade. If it sits in a tail, the tail will be real, not a poetic invention. There is a deeper gift. Repetition reveals evolution. Some surveys will track the same object for many months. In those strings of measurements, you can watch how chemistry changes with distance, how light curves breathe with rotation and with season, and how motion responds to outgassing. You can build priors that are rooted in real ensembles. Then you can apply those priors to new arrivals in a way that is honest. The seed idea will benefit from this library. If many visitors show volatile profiles that favor early carbon dioxide release, and if those same visitors shed fluffy grains that polarize light in similar ways, the case for ready-made cores becomes more than a thought experiment. It becomes statistics. Selection effects will still haunt us, but we will be able to measure them rather than guess at them. Bright objects bias the list. Active comets bias the list. Vantage geometry biases the list. With enough entries, we can model these filters and pull them out. Then the counts will tell us how many dark wanderers likely pass through without any wake at all. That number matters for capture theory. A young disk does not care whether a seed was bright. It cares whether the seed is there to be slowed and kept. Known meets unknown and the balance shifts slowly. Known, high-cadence surveys increase discovery rates of moving objects across the board. Known, software that compares images can propose orbits quickly enough to direct telescopes while the light still cooperates. Unknown, the true abundance of interstellar visitors in the kilometer class and below. Unknown, the fraction that carry carbon dioxide-rich skins or deep water layers. Unknown, how often dust that has lived between stars will show the same strong polarization branch that we see today. Our through line remains simple. Let motion and light tell one story together, and do not let either outrun the other. The census will not solve every argument, but it will change the ground under our feet. It will lower the volume on claims that ride on romance, and raise the signal from claims that ride on numbers. It will make it easier to say this case is ordinary in these ways and unusual in these. It will help instrument teams close the loop faster when something strange peaks above the noise, because they will have a bank of analogues ready for comparison. Most of all, it will make the next visitor feel less like an apparition and more like a neighbor you expected to see at last. Which brings us back to the calendar that we already have. The first close hearing near Mars, where a different kind of repetition waits, rotation after rotation, jet after jet, angle after angle, until a clean pattern either emerges or dissolves. Court opens over a red world. Mars does not judge, it witnesses. A cluster of orbiters, built to read dunes and ice caps and faint vapors above a thin sky, now turns its lenses outward. The visitor does not sweep close enough to be dramatic, yet the geometry is generous. No thick earth air to smear fine structures, no day-night interruptions to break cadence every few hours. Just long, steady looks across multiple rotations, a chance to watch the machine of sunlight and spin tick through its steps. This is how small mysteries yield, not to a single heroic exposure, but to repetition that refuses to blink. Start with morphology. A sun-facing fan should breathe in tempo with local noon. As the nucleus rotates, vents will enter daylight, warm, and fire. They will then slide into dusk, cool, and rest. If the rotation period is short, the fan will pulse with a crisp beat. If it is long, the beat will be slow and heavy, with substructure as small events contribute. Mars, with its extended viewing runs, can fold images over many cycles and see whether features return to the same. Clock ticks. One possibility is that the fan will shift in direction as new active areas catch up to the sun and old ones fall away, a natural choreography that maps to a spinning globe. A competing view suggests that a pattern might hold a heading through expected night intervals. That would be the first flag for control. It remains uncertain whether subtle topography or thermal inertia could mimic such defiance. This is why angle diversity matters. Mars can watch the same surface under slightly different phase angles across days and expose tricks that geometry plays. Now the color of the breath. Spectrometers aboard Mars orbiters do not match the reach of the largest space telescopes. Yet, they carry a precious advantage. They work above nearly all atmospheric absorption. Water-related fragments that are muted in Earth, spectra, can be clearer here. Carbon dioxide features can be tracked as the plume waxes and wanes. The question is not only which molecules appear, but how their strengths change with rotation and with distance from the nucleus. If water-linked signatures spike only when specific vents turn into sunlight, that respects thermal logic and supports a layered or cracked interior. If carbon dioxide holds a flaw that does not care about local noon, that would surprise. Evidence is limited, but one inference is that the Mars window can catch quick transients that would smear away in longer Earth-based integrations. Polarimetry is harder from Mars, yet some instruments can pull partial information about scattering behavior by sampling light at multiple angles with narrow filters. Even crude estimates help. If the negative polarization branch remains deep and wide across rotations, the coma is dominated by fluffy grains that launch easily from a small body. If the branch varies with time or with geometry more than expected, deeper questions about grain populations arise. These details feed back into jet modeling. Fluffy grains ride gas differently than compact grains. The way they arc and settle shapes the fan, and that shape helps estimate the rotation state without seeing the nucleus directly. Motion hides in plain sight, even here. Mars cannot track the global orbit better than a network of ground stations and space telescopes, but it can measure relative motion of coma structures with exquisite detail. Jet features that drift across the field become traces of rotation. If the same filament appears at the same place in phase space over many cycles, that consistency will refine the spin period and hint at precession if peaks wander slowly. A minority view holds that such fine structure is too delicate to use at these distances. That view underestimates what patience and stacking can do. Align dozens of frames on the photocenter, subtract a smooth coma model, and faint ribs of activity step forward. What looked like fog becomes an atlas of vents. Known meets unknown with helpful boundaries. Known, Mars orbiters can sustain long sequences that Earth observatories cannot, which is ideal for timing tests. Known, freedom from terrestrial air opens a clearer lane for faint volatile lines. Known, repeated imaging across rotations is the right tool to expose jet maps that obey sunlight or ignore it. Unknown, whether the rotation period is simple or complicated by torques that change it over weeks. Unknown, whether water-linked lines at this distance will sit above instrument thresholds. Unknown, whether jet directions will drift exactly as thermal models predict, or will occasionally hold as if something steadied them. Our through line remains simple. Let motion and light tell one story together, and do not let either outrun the other. There is a human rhythm inside this window too. Teams negotiate pointing time. Schedules flex. Data packets ride radio paths to Earth, then to centers where pipelines clean, calibrate, and flag anomalies. The most valuable product will not be a single dramatic image. It will be a stack of aligned frames and a set of folded light curves with clear error bars. That stack can be shared across the community. It will become the baseline against which perihelion behavior is compared, and the reference that December spectra will seek to confirm or revise. If the Mars hearing ends with jets that keep solar time, with water that speaks in pulses that match daylight, and with carbon dioxide that leads but still responds to heat, the natural story gains ground. If instead one filament keeps pointing through night, if one ratio holds stubbornly flat despite swings in temperature, if one faint spectral feature repeats where known molecules do not belong, then the checklist for technosignatures earns attention. Either way, the value is the same. Speculation stops floating. It ties itself to a phase, a period, a number that anyone can test. The court then recesses as the object vanishes behind the sun, and we prepare to listen in a different way when the stage lights rise again. Perihelion is the loudest scene staged in a room we cannot enter. From Earth, the sun is a white curtain that swallows the actor just as the script promises fireworks. That does not mean silence. Coronagraphs carve a dark hole into the solar glare and watch anything that trespasses the streamers. Inner system probes stare across angles that ground observatories cannot reach. Instruments tuned for the wind, and the corona become comet watchers for a brief season. The visitor rushes through maximum heat, Volatiles should leap from shadowed pores. Dust should thicken and drift into sculpted fans. If there is any hidden clock in the object, this is where it must keep time without flinching. Think of the environment as a crucible. Solar radiation floods the surface. Temperatures rise fast. The thermal skin deepens by a few precious centimeters, enough to recruit layers that slept through the Mars window. One possibility is that water signatures strengthen relative to carbon dioxide as deeper pockets awaken. A competing view suggests that a thick carbon dioxide crust can dominate even here, smothering the water signal until well after closest approach. It remains uncertain whether organics will step out of the haze at these distances, or whether they will wait for cooler nights in December. Evidence is limited, but one inference is that the shape and color of the coma near perihelion will set the tone for everything that follows. Geometry forces new methods. We cannot rely on long-slit spectra from flagship telescopes during the days the sun blocks our line of sight. We lean on radiance maps from coronagraphs that are designed to reveal faint structures in the bright solar neighborhood. We lean on imagers aboard probes that live inside or near the orbit of Mercury. Even modest cameras can win here because the angles are kind. A faint tail that would drown in the glare from Earth can stand out when seen from a different perch. Time resolution matters more than absolute depth. If jets strobe, if fans flip from one quadrant to another in a beat that ignores local noon on the nucleus, that is a pattern that survives thin data. Cadence is our ally when integration time must remain short. There is also a chance to watch the object talk to the solar wind. Small grains charge quickly in this environment. Ion tails weave and break as fields shift. An engineered system that cares about stability might try to resist these forces or to ride them in a way that keeps a preferred attitude. Natural bodies usually submit. The fan flows with heat. The ion structures dance with the wind. A minority view holds that clever camouflage could time activity to pass as natural even under stress. That is a claim that fades if the wind writes rough rhythms across the coma, yet the orbital residuals stay quiet and stubborn in one direction. Motion and light must tell one story together, or the discrepancy will point. Our through line remains simple. Let motion and light tell one story together, and do not let either outrun the other. Perihelion can also expose fragility. Some comets shed shells or fragment under rapid heating. If the visitor holds itself together through this episode, that resilience will inform the living technology, thought experiment, and the seed idea in different ways. One possibility is that resilience arises from microstructure alone. Porous frameworks can flex to relieve stress. Fractures can open in controlled patterns that vent pressure before it builds. A competing view suggests that resilience might hint at designed self-regulation in the surface layers. It remains uncertain whether we can discriminate between those outcomes with partial imagery. The best clue will be continuity. If morphology before and after perihelion looks like the same engine warmed through and cooled down, natural explanations gain weight. If a new regime appears and then persists with suspicious steadiness, curiosity must lean closer. What matters most is how the object exits the glare. The first clean spectra in December will arrive with a memory of perihelion baked into the ratios. If water lines come up in strength as models predict, the layered interior survives as the leading story. If carbon dioxide remains dominant without relief, we revisit the map of birthplaces and the possibility of persistent processing on the skin. If unexpected narrow features appear and hold across instruments, then the checklist for techno-signatures turns a page. Perihelion does not finish debates, it primes them. It sets boundary conditions that the next window will test. There is a practical beauty in this hidden act. We learn to treat absence as a parameter, not as a void. We plan what counts as a change worth naming. We decide in advance what ratios must move for a hypothesis to breathe. That discipline will pay off when the curtain lifts and cold detectors can finally read the light without the sun in the frame. The traveler will not wait for our convenience. It never has. We meet it with the tools that can still see and with the patience to compare before and after without trying to fill the blackout with easy fantasies. When the object clears the glare and the December geometry improves, the stage will belong to spectrographs again. The story that perihelion wrote in heat and stress will either expand or shrink. In that transition, we will learn whether the mystery is deep or only sharp-edged from a distance. Either way, the next beat is ours to catch. December is where the blackout ends and the ledger opens. The geometry softens, the coma relaxes from its day in the furnace, telescopes that slept during perihelion wake into cold nights, and spectrographs drink deeply from a light that now carries the memory of stress. This is not a time for fireworks. It is a time for accounting. What changed? What held? Which lines grew bold and which lines went quiet? The answers will either fold our traveller back into the patient logic of thermal layers or send us hunting for mechanisms that refuse to care about the Sunday. Begin with the big duet, carbon dioxide and water. Before perihelion, the balance leaned hard toward carbon dioxide while water chemistry appeared early in delicate traces. After a deep warming, you expect the script to adjust. One possibility is that water lines rise in strength as deeper pockets wake, while carbon dioxide remains present but yields some territory. A competing view suggests a stubborn skin that continues to favor carbon dioxide even after heat should have thinned barriers. It remains uncertain which way the ratios will move, but the test is clean. We measure the same object at similar distances, with a different thermal history. If the mix evolves, layering wins. If the mix resists, then surface processing or unusual pore networks take center stage. Organics hide in the margins, but December is their chance to step forward. Complex molecules are faint and crowded by neighbors in the spectrum. Lower background and patient integration help separate them. Evidence is limited, but one inference is that perihelion can liberate heavier species from pockets that were sealed at larger distances. If fresh bands appear in the infrared, and if they vary with time in step with cooling, that supports a natural interior where chemistry is arranged by volatility and depth. If faint lines cluster near wavelengths that do not suit known molecules, and if they repeat across instruments, the checklist for technosignatures earns a cautious mark without a claim. The rule holds. Many confirmations across many nights, or it does not count. Polarization can change as the coma repopulates. Fresh grains lifted after perihelion may carry different textures than the weathered population that dominated before. A deep negative branch could relax if larger or more compact grains take over. It could deepen if fluffy aggregates from new vents flood the field. The subtlety matters. A curve that shifts in step with other evidence for new material points to dust as a faithful recorder of interior history. A curve that refuses to move while chemistry clearly evolves would ask harder questions about dust creation and evolution. December lets us make this comparison without the glare that complicates earlier attempts. Motion is quieter here, but not silent. Non-gravitational forces will fade as activity drops, yet careful fits can still weigh the tail of the perihelion thrust. If residuals that were noisy before now settle toward zero in a way that tracks the decline in outgassing, that supports simple models. If a bias lingers with a stable heading unrelated to sunlight, the case for control grows. The Jupiter leg will be the harsh judge for dynamics, but December can already whisper which way the hearing will lean. Isotopic ratios are the slow music beneath the scene. Deuterium to hydrogen in water, carbon-13 to carbon-12 in carbon dioxide, nitrogen-15 to nitrogen-14 in cyanogen. These numbers do not swing wildly with season. They point to birthplace more than to weather. December spectra can begin to bracket them if the lines are clean and the models of temperature are honest. If ratios diverge from solar system norms by generous margins, the case for a cold, distant nursery strengthens. That does not make the object a seed by itself, but it aligns the chemistry with the conditions that a seed story prefers. Known meets unknown in the quiet of long exposures. Known, post-perihelion observations have the leverage to confirm or revise early impressions without the distortions of solar glare. Known, stronger waterlines, after heating, would fit stratified interiors that many comets share. Known, organics often ride behind larger drivers and need patience to see. Unknown, whether this traveller will follow the script or insist on its own rhythm. Unknown, whether narrow features will scuff the catalogues and survive checks. Unknown, whether dust behavior will track chemistry with the elegance that models predict. Our through line remains simple. Let motion and light tell one story together, and do not let either outrun the other. There is also the matter of mood. December is when speculation should change shape. We are no longer guessing across a curtain. We are comparing before and after with the same instruments, the same pipelines, the same teams. That continuity kills excuses. If water rises, we say so. If carbon dioxide holds the crown, we say so. If organics appear at last, we map them in time and see whether they keep thermal hours. If nothing surprising happens, that is a result with weight. It says that odd can still be stable, and that stability needs no secret plan to explain it. The window will close in its own time. As distance grows, lines fade, and scheduling fights grow harder to win. But the pages written here will follow the traveller to the next exam. Jupiter waits ahead with gravity and radiation that do, not negotiate. December is where we sharpen our pencils and write the predictions that exam will grade. If the numbers earn a passing mark, the natural story gains a new branch, the seed story gains a new ally, and the artifact story loses some breath. If the numbers refuse our expectations, then curiosity gets another season in the Sunday Jupiter does not negotiate. Its gravity is a ruler with no sympathy. Its radiation belts a furnace that tests every fragile idea we have about dust and gas. When the visitor enters this domain, the mathematics tighten and the room for flattering stories shrinks. A close approach, not a grazing whisper but not a dive either, gives us leverage that earlier windows could not. Trajectory fits, snap taut. Tiny forces that hid inside earlier uncertainties step into the light. If sunlight and sublimation alone have steered the small residual pushes, the curve will behave like an obedient arc bent by a giant. If any guidance hides beneath a comet costume, the bend will not quite match the script. Begin with the measurement itself, precise time-stamped positions strung along the track like beads. Dynamicists predict the path using gravity from the sun, the planets, and the known mass distribution of the system. They add small terms for outgassing if earlier data merit them. Then they compare the prediction to reality. One possibility is that the difference between prediction and observation shrinks dramatically during the Jovian segment. Because geometry amplifies sensitivity, and because many lines of sight converge on the same small patch of sky. A competing view suggests that coma brightness and tail structure may complicate centroiding just when we crave perfection. It remains uncertain where the practical floor of accuracy will land for this pass. Evidence is limited, but one inference is that even a modest improvement in precision will act like a magnifying glass for any bias that keeps a steady heading. Radiation changes the texture of the test. Charged grains behave differently near Jupiter. Ion tails twist and reconnect with a swagger that calm solar wind regions rarely display. The coma can sharpen, then fray, in response to field changes that have nothing to do with heat. For a natural comet, this is theatre without intention. For any system that tries to regulate attitude or maintain a preferred spin, this is a stress test. If vents act as stabilizers, if porosity self-adjusts to keep torques within bounds, those responses must operate inside a storm of charged particles. We will watch for continuity. Does the fan recover a familiar shape after each jolt? Do rotation-linked features reappear on schedule despite the electromagnetic roughness? If so, resilience may be structural rather than guided, a property of foamy layers that flex and vent rather than a hidden piloting law. Gravity also opens a window into the mass distribution of the nucleus. A perfectly rigid point mass takes a path that we can model to exquisite accuracy. A loose aggregate that sheds or rearranges material under stress will subtly alter its own trajectory by changing how outgassing thrust couples to spin and shape. The timing of small brightness variations can then feed back into the orbit fit. If multiple teams can agree on a rotation period and can track how it drifts during the approach and the exit, the pattern of drift becomes a probe of internal structure. A compact, coherent body should show smooth, predictable changes as jets torque it. A rubble pile might lurch or present beat notes that change unexpectedly. Neither outcome implies design. Both outcomes tell us what kind of stone we are really following. Our through line remains simple. Let motion and light tell one story together, and do not let either outrun the other. Non-gravitational acceleration has its best chance to confess here. Earlier in the journey, Residuals had wider shoulders. Small biases could hide inside noise. Near Jupiter, a bias that keeps the same sign across many hours becomes hard to dismiss. One possibility is that the residuals will fall in line with models that scale naturally with activity level and solar angle, then decline again as the visitor recedes and cools. That would be the clean signature of sublimation physics doing its ordinary work under extraordinary gravity. A competing view suggests a bias could persist with a heading that does not track local noon, a gentle insistence that hints at control. If such a bias appears, the community will try to break it with every systematic they can imagine, from centroid shifts due to coma asymmetries to catalogue errors in background stars. Only when those trials fail will the word artificial earn a seat at the table. There is a quieter payoff too. Gas and dust that pass through the Jovian magnetosphere may change in ways that help interpret earlier anomalies. Polarization curves could shift if grains acquire charges that alter how they clump or break. Spectral lines from certain ions might brighten in response to energetic electrons. If we see these effects and if they align with models of the environment, then odd behavior attributed to intent elsewhere may instead be fingerprints of context. The gauntlet, in other words, can erase mirages by forcing everything to respond to the same external drama. Known meets unknown with sharper teeth. Known, a strong gravitational field allows sensitive tests for tiny deviations from predicted motion. Known, Jupiter's radiation field can reshape coma behavior on short timescales without any need for special pleading. Unknown, whether centroid precision and cadence will reach the floor needed to expose a small but persistent thrust unrelated to sunlight. Unknown, whether rotation state will stay calm or drift in ways that hint at internal complexity. Unknown, whether transient ion features will confuse or clarify our reading of spectral and polarimetric data. What would a decisive outcome look like? If trajectory residuals collapse to near zero after accounting for standard outgassing models, if rotation changes track jet-driven torques, if the coma's response to radiation matches expectations, then the natural story advances with confidence. The seed idea remains alive, enriched by a fuller chemical biography and by resilience under stress. If instead a stable non-solar bias in motion survives every correction, if light curves show timed steps that hold through geometry changes, if narrow spectral spikes appear and repeat, then the techno-signature checklist turns from theory into report. Either way, Jupiter's pull writes the cleanest lines we will get in this case. Beyond the numbers sits the simple human truth. A giant planet gives us a moment when the universe itself tightens the instruments for us. We should meet that gift with caution and courage in equal measure. When the visitor leaves the Jovian gauntlet and the residuals are tallied, we will be ready to place our findings on the decision tree that has waited since the first frames, and to follow its branches without flinching. By now, the investigation has grown branches. Each new measurement, each tightened residual, each stubborn ratio pushes us down a path. Rather than pretend that one clue will crown a winner, we lay out the forks and walk them with discipline. 3 destinations wait at the far end: a natural comet that broadens our catalogue, a natural seed that solves a timing problem for giant planets without asking for intention, an artifact whose camouflage fails under patient light. The decision tree does not care which answer is most dramatic. It only cares which sequence of tests survives contact with the sky. Start with the trunk of the tree, motion. If non-gravitational accelerations collapse into patterns that follow solar angle and rotation period across all windows, the artifact branch loses major ground. Jupiter is our harshest judge for this, and December provides the rehearsal. One possibility is that a small bias will tease at significance around perihelion, only to fade as activity ebbs. That is the behavior of vents, not vectors chosen by design. A competing view suggests that a whisper of control could ride inside sublimation noise, and only the Jovian segment can expose it. It remains uncertain where the final floor of precision will land, but we have set a threshold. If a stable heading persists through rotation and phase changes, we walk right. If not, we keep left. Next comes chemistry and its evolution. Before perihelion, the carbon dioxide voice was loud. Water spoke in delicate traces at distances where it seldom sings. After perihelion, December writes a verdict in ratios. If water lines grow as deeper pockets warm, and if carbon dioxide yields a little territory without vanishing, we have a layered interior that aligns with many natural comets and with the seed idea. If instead the mix stays strangely constant across wide swings in heating, the tree asks a hard question. Is there a natural process that freezes the recipe, perhaps a crust that regulates permeability, or are we watching a composition held steady on purpose? The branch does not snap from one twig. We require repeated spectra, stable across instruments, before we climb higher. Dust and its optical confession form the third test. Polarization that sits deeper and longer in the negative branch points to fluffy aggregates and to grains altered by long interstellar weathering. If that curve shifts after perihelion in step with other evidence for fresh material, the dust is behaving like a recorder of history rather than like a tuned cloak. If the curve ignores the arrival of new grains while chemistry clearly evolves, the branch bends towards suspicion. A minority view holds that geometry alone can flatten or deepen curves in confusing ways. That is why cadence and angle diversity matter. Mars supplied rotation-rich sequences. December supplies clarity. Jupiter supplies stress. We do not climb the branch on a single night. Our through line remains simple. Let motion and light tell one story together, and do not let either outrun the other. Now we weigh the destinations. The natural comet destination is already sturdy. The object outgasses, builds a coma, throws a sun-facing fan, trails a faint tail, and obeys gravity when gravity gets loud. Unusual chemistry and dust stretch taxonomy, but they do not break it. That path ends in a wider, wiser catalogue. The natural seed destination is a refinement, not a leap. If volatile layering, early carbon dioxide activation, fluffy grains, and resilience under heating all hold, then the body has exactly the traits that a young disk could exploit. This does not mean capture happened here. It means capture would have worked elsewhere, and often enough to matter, which is a satisfying answer to a long-standing problem. The artifact destination remains the steepest climb. It asks for converging signatures that natural models cannot imitate, a sustained, non-solar bias in motion, timed brightness steps that ignore rotation and survive geometry changes, narrow spectral features that repeat outside known molecular catalogues, dust behavior that refuses to track the arrival of new material. One or two of these could still be tricks of context. All of them together would be a confession. We have not heard that confession yet. The tree keeps the door open, but it does not carve the door wider just because the room behind it is exciting. There is a final branch we rarely name out loud, the humility branch. It says that our census is still thin, our models are still young, and our appetite for intention runs ahead of our patience. One possibility is that the most remarkable lesson of this visitor will be how well ordinary physics can be dressed by unfamiliar chemistry. A competing view suggests that the seed idea will graduate from speculation to staple once surveys fill in the population, and exoplanet chemistries echo imported heritage. It remains uncertain which story will own the epilogue. What is certain is the value of the tree itself. It prevents us from sprinting down one path when the footprints have not chosen a lane, so we keep walking with rules that do not bend. Motion first, evolution of chemistry second. Dust that agrees or disagrees with both. Each new window will not rewrite the map, it will shift our weight from one branch to another. When the last measurements are in, we will not need a dramatic reveal. The branches will have placed us where the data belong, and the ending will feel inevitable only because we refuse to skip steps. If chemistry tells us what is on stage, isotopes tell us where the props were built. Ratios are the quiet cartographers of the cosmos. Deuterium to hydrogen in water, carbon-13 to carbon-12 in carbon dioxide, nitrogen-15 to nitrogen-14 in cyan-bearing species, oxygen-18 to oxygen-16 in several lines. These numbers do not leap with weather, they lean toward history. They record the temperatures and radiation fields of the nursery, the way molecules froze out, and the cycles of processing that followed. For an interstellar visitor, this is the closest we get to a postage stamp from its first address. Begin with water, because it carries the sharpest thermometer. Deuterium prefers colder chemistry. In regions far from a star, reactions enrich ices with deuterium relative to hydrogen. One possibility is that our traveler will show a deuterium to hydrogen ratio higher than most solar system comets, a hint that it's water condensed in more distant or older zones. A competing view suggests that internal mixing and later processing can blur that signal, especially if layers formed at different epochs now vent together. It remains uncertain whether December spectra and later observations will have the signal-to-noise required to isolate the ratio cleanly. Yet even a bracket can gape-hide, push the birthplace map toward or away from familiar ground. Carbon is a second compass. Carbon-13 to carbon-12 varies across stellar neighborhoods and across time. Carbon dioxide lines in the infrared can carry enough structure to tease out that ratio when temperatures are modeled honestly. If the value sits outside the solar system norm by a generous margin, that argues for a molecular cloud history that did not match our own. Evidence is limited, but one inference is that a carbon dioxide strong coma provides more leverage here than a water-dominated one, which means this object is a good candidate for a carbon isotopic test. If the ratio lands close to local values, that does not erase difference, but it narrows which regions of the galaxy are plausible birthplaces. Nitrogen is trickier but valuable. Nitrogen-15 to nitrogen-14 in cyanogen or in hydrogen cyanide can separate chemistry that lived under different ultraviolet fields. A minority view holds that nitrogen measurements are too model-dependent to anchor strong claims for a case like this. That caution is fair. It is also true that multiple isotopic systems working together can overcome the weaknesses of each. If water, carbon, and nitrogen all tilt in the same direction away from local norms, the map gains lines that are hard to ignore. Oxygen carries a quieter clue. Oxygen-18 to oxygen-16 helps test whether the water we are seeing comes from a reservoir that matches known solar nebula fractions. Deviations can arise from fractionation in very cold environments. If the oxygen ratio wanders with distance while the deuterium ratio stays steady, that may reveal layering in which different ices feed the coma at different times. If both remain steady across the season, the interior may be more mixed than we hoped. Known meets unknown with patient arithmetic. Known isotopic ratios change little on month scales, so they are robust against daily fluctuations in activity. Known, our best instruments can reach these lines if the coma is not too faint, and if temperature models are tied down by multiband spectra. Unknown, whether blending with neighboring lines and with dust continuum will blur the results enough to make only loose constraints possible. Unknown, how much the perihelion heating shuffled the deck of venting layers, which can mix histories in ways that complicate clean readings. One possibility is that the isotopic map will align with the seed idea, a colder birth environment, recorded in deuterium enrichment and in oxygen fractionation, would fit a body that began life beyond the familiar snow lines of many systems. A competing view suggests that even a cold signature does not imply seeding, it only describes origin. The capture story would still need population statistics and dynamical arguments to carry weight. It remains uncertain whether isotopes alone will make anyone switch branches on the decision tree. They are not verdicts, they are biasing evidence, gentle but persistent. There is also the promise of comparisons. The first quiet visitor that refused to grow a bright coma left little room for isotopic work. The second, an ordinary comet by many measures, offered ratios closer to our experience. If the third adds a different set of values, we are already building a small atlas that future arrivals will join. Over time, those points will cluster in ways that reveal families and outliers. The next time a carbon dioxide-rich traveler appears, we will check whether its isotopes live in the same quarter of the map. If they do, we can treat chemistry and isotopes as a package, rather than as separate curiosities. Our through line remains simple. Let motion and light tell one story together, and do not let either outrun the other. Isotopes can also rescue us from theatrics. Narrow spectral features that look exotic can be cross-checked against isotopic shifts of known molecules. A spike near a familiar band that sits at an offset consistent with a heavier isotope is not a calling card from a device, it is a textbook line moved by mass. In the same way, a ratio that defies every known chemical pathway is not a myth. It is a flag that our catalogue missed a path or a place. Either way, the work turns spectacle into measurement. When the isotopic ledger closes for this object, we will have either widened the circle of what local physics can explain or marked a dot on the galactic map that does not overlap our neighbourhoods. Both outcomes are worth the time. One grounds the seed idea with chemistry that helps a young disk. The other turns a single comet into a messenger from a climate we seldom sample. In both cases, the ratios take wonder and make it testable. That is their gift and their warning. They ask us to slow down, to count, to compare, and to let origins whisper instead of shout. Zoom out, and the mystery stops being only about one traveller. It becomes a rehearsal for how we respond to anything rare that crosses our sky. The stakes braid together science, safety, and story. A natural comet with unusual chemistry stretches our models and calibrates our instruments. A natural seed would nudge planetary theory, linking quick core growth to a traffic of imported bodies that young systems can capture. An artifact would reorder policy and culture at once. You do not prepare for such a spectrum of outcomes with a single plan. You prepare by agreeing on rules before the adrenaline arrives, then by learning to communicate in a way that keeps wonder honest. Begin with planetary defense, because it is the most practical. Even peaceful rocks become hazards if their paths cross ours. Interstellar visitors in the size class of our traveller are not threats in this pass, yet they challenge tracking and modelling. One possibility is that techniques developed to watch 3 IATLAS, cadence, rapid orbit refinement, and coordinated spectroscopy, will feed directly into how we handle a future object on an unfriendly path. A competing view suggests that interstellar speed makes many defense options moot, since deflection requires time we may not have. It remains uncertain which tools scale well to fast intruders. Evidence is limited, but one inference is that practiced networks and pre-planned data sharing improve every outcome, even when the object is harmless, because muscle memory turns panic into protocol. Now consider SETI, a field built on patience and on listening rather than on chasing. The artifact hypothesis, however unlikely on present evidence, forces a useful shift in posture. Instead of waiting only for narrowband radio or optical beacons, we also watch for physical techno-signatures in our own backyard. That does not mean declaring victory when a light curve looks odd. It means expanding the menu of tests, then tying them to a checklist that the community has endorsed in public. If the checklist stays mostly red, skepticism keeps its seat. If several boxes turn green across independent instruments, then a message to the world does not sound like a rumor, it sounds like a measured finding. The point is not to sensationalize the sky. The point is to be ready to move from maybe to yes without fumbling the handoff. Policy sits in the middle and dislikes surprises. Agencies and observatories can use this case as a live drill. Who coordinates when data streams touch many domains? Who speaks first when a claim might spark headlines? How do we label preliminary results so that updates feel like progress rather than reversals? One possibility is to publish tiered advisories, facts, preliminary interpretations, and speculative avenues, with clear timestamps and owners. A competing view suggests that transparency invites chaos. Our experience argues that secrecy invites louder chaos. It remains uncertain whether every partner will accept the same protocol. The lesson of many campaigns is that shared playbooks beat improvisation, especially when the audience is global and the rumors move faster than light. Communication is not decoration. It shapes what the public learns to expect from science. If every anomaly becomes a promise, trust erodes. If every anomaly becomes a scold, curiosity dies. The middle path is to narrate the known and the unknown as characters that share the stage. We show the calendar, the Mars hearing, the perihelion blackout, the December ledger, the Jovian gauntlet. We name the tests before the answers arrive. We live with our own predictions in the open. When the results come in, we keep score in public. That habit does not dilute wonder, it protects it. Audiences can enjoy cinema and still love the truth that emerges from patient frames. Our through line remains simple. Let motion and light tell one story together, and do not let either outrun the other. There is a cultural stake that refuses to be small. People ask what it means if worlds are seeded by travelers from other nurseries. People ask what it means if a disguised device can cross a system and leave almost nothing but questions. The honest reply is that both answers make us larger. A seeded cosmos makes our planets cousins by chemistry. A watched cosmos makes our choices heavier, since silence might be prudence and contact might be risk. Either way, dignity grows when we name our ignorance and measure it instead of hiding it behind certainty. The final practical stake is simple to state and hard to fund. We need a mission that can meet a future visitor up close. Interceptors on patient orbits, small spacecraft that wait near regions of easy escape speed, instruments built for fast approach and fast handoff. The cost is not small. The return is a sample of how to plan for the unknown, delivered on a timetable set by physics rather than by our budgets. A minority view holds that telescopes are enough. The counter is that surfaces lie at a distance, and that touch can end arguments that light alone only moves. One day, a traveler will arrive with warning that fits a mission already waiting. If this case helps write the requirements for that day, the exercise will have paid for itself in advance. So, the stakes are not only scientific conclusions, they are rehearsals for skill, for humility, for public speech, and for shared courage. This traveler teaches by being strange and by being reachable at the same time. If we let it, it will leave us with better tools, cleaner habits, and a wider sense of who shares this galaxy with us, even if the only company we confirm is chemistry older and colder than our own. There is a feeling that arrives before the numbers. It lives in the small space between a first image and the first explanation. Wonder rushes in, fear walks behind it, patience tries to take both by the hand. Our visitor has offered that feeling again and again. A glow that looked like a headlight, a chemistry that speaks in an unusual accent, a path that reads like a calendar. Each moment tempted us to sprint toward a story that felt right. Each window also brought the reminder that the sky does not owe us drama, it owes us light and motion. We owe the rest to discipline, to craft, and to a quiet respect for how slow certainty travels. Wonder is the spark. It pulls late nights from tired eyes and fills notebooks with questions that barely fit on the page. It makes a research team stand in the cold, waiting for a clear patch, and gives a writer the courage to say, "What if?" and still mean it kindly. Without wonder, the calendar of Mars and the Sun and Jupiter would be a checklist with no heartbeat. With wonder, it becomes a journey whose stops feel earned. The danger is simple. Wonder prefers closure. It looks for patterns, and it celebrates intention. The sky is richer than that. It allows beautiful accidents. It favors coincidences because coincidences are plentiful when space is large and vision is sharp. Fear is the weight. It whispers that an object could be a scout. It wonders if a seed might carry more than chemistry. It asks whether hidden engines might move when we cannot see. Fear is not shameful. It keeps questions sharp. It shouts when someone tries to turn doubt into insult. It also needs a leash. If fear sets the headline, every thermal fan becomes a beacon and every odd ratio becomes a code. That is not respect. That is superstition with better fonts. Fear belongs in the room, but it does not get the chair at the center. Patience is the rhythm section. It keeps time while solos soar. It lets Mars collect rotations until a beat appears. It lives through the perihelion blackout by trusting coronagraphs that were not built for this story. It returns in December and counts the ratios without rooting for a side. It enters the Jovian gauntlet with quiet confidence that gravity will write in firm lines. Patience also knows when to speak simply. This looks like a comet. This behaves like a seed would behave if a young disk wanted a head start. This does not yet behave like a device. Patience makes those sentences feel like progress rather than like a retreat from spectacle. Our through line remains simple. Let motion and light tell one story together, and do not let either outrun the other. There is a human thread that ties all of this to the ground. A student who saw the first frames will grow into an observer who writes the proposal that wins the next window. A technician who learned to nurse a tired detector through cold nights will write the checklist that saves a crucial run for someone else. A family that watched the updates together will set their alarm for a meteor shower with new respect for how a faint streak is a book with pages we can read. The object will leave. The habits will stay. That is how a single traveler changes a culture gently and for a long time. This is also a story about permission. We can give ourselves permission to enjoy mystery without declaring answers. We can let a scene be cinematic without letting the camera lie. We can hold 3 ideas in our hands at once: natural comet, natural seed, engineered artifact, and let evidence move our fingers rather than our taste. We can allow each faction in the audience a moment of recognition. The romantic can have the music, the engineer can have the checklist, the child can have the gasp. No one needs to lose if the ending is a careful sentence that begins with what we know. There is one more kindness we can do for the future. We can write our predictions plainly and in public. We can say which lines should rise in December if layering rules. We can say how residuals should behave near Jupiter if sunlight is the only pilot. We can say what narrow features would count as strange if they repeat across instruments. Then we can accept the results with the same voice we used to frame the tests. That habit teaches an audience that science is not a contest between egos. It is a conversation between nature and questions that were posed with care. When the traveler fades, the feeling will remain. Wonder will still be a spark. Fear will still be a weight. Patience will still be a drum. The next mystery will step onto the same small stage. We will greet it with a steadier hand because this one made us practice. That is the quiet victory we can claim now, before any final verdict arrives. We learn to look closely and to speak carefully, while the night was loud. We learn to enjoy the theatrical without surrendering the true. The sky will reward that posture again. Here is the table we promised to set. 3 plates, 3 honest servings, no garnish that pretends to be proof. The first plate holds a natural comet that happens to be chemically unusual. The second holds a natural seed whose properties match what a young disk would love to capture. The third holds an artifact that wears stone and snow to pass among worlds. We have spent the journey asking what light and motion will allow us to place on each plate without borrowing. From taste, we can now pour what we have into sentences that you can repeat without apology. Begin with what is strongest. The object behaves like a comet in its broad strokes. It follows a hyperbolic path. It outgasses in a way that creates a sunward fan and a faint anti-solar tail. It shows early water chemistry through hydroxyl at large distance. It speaks carbon dioxide more loudly than most local comets. Its polarization curve reaches deeper into the negative branch than many examples from our backyard. Size estimates place the nucleus in a modest kilometer range. None of these facts alone climb to a headline. Together they make a coherent portrait that belongs in the natural catalogue. If December shows water rising after perihelion as thermal models predict, and if the Jovian segment brings residuals that collapse when we account for sunlight and rotation, then the natural verdict is not only safe, it is elegant. The seed version of natural asks for a little more. It asks that the same portrait happen to match a role in planet making. On that score, the traveler's traits line up neatly. Carbon dioxide dominance lets the body breathe at greater distances, which increases collision cross-section in a young disk. Fluffy grains inferred from polarization leave the surface easily, stick readily, and help build mass around a captured core. A small nucleus preserves stratigraphy that can release waves of different volatiles as heat penetrates. If isotopic ratios tilt toward colder formation zones, that strengthens the case that this chemistry was born in a nursery far from a central star. None of this proves that capture occurred here. It shows that capture would have worked elsewhere many times. If surveys confirm that such travelers are common, the seed path moves from story to staple. Our through line remains simple. Let motion and light tell one story together, and do not let either outrun the other. The artifact plate stays the hardest to fill. It demands signatures that resist every natural script we can write. A persistent non-solar bias in motion that survives rotation and geometry changes. Timed brightness steps that ignore thermal logic. Narrow spectral lines that repeat away from known molecules after checks for contamination. Polarization that refuses to evolve even when fresh dust clearly enters the coma. We have not seen that confluence in the record we have. A few edges look sharp at first glance. Better images turned a headlight into a sun-facing fan. Wider context placed an elegant itinerary back inside selection effects. The door is not locked, it is simply closed for now. It would open if several boxes on the checklist turn green at the same time, under independent eyes. So the verdict you can hold today is layered. Most likely, a natural comet that widens our sense of what interstellar chemistry can be. Plausibly, a natural seed whose traits support a faster path to giant cores in busy nurseries. Unproven, an artifact with intentions that our instruments must compel rather than imagine. The value is not in a drum roll. The value is in knowing why you believe the sentence you repeat. The next windows will push the weight a little further along the branch you favor. December will grade our expectations for how ratios evolve in a cooling coma. Jupiter will grade our expectations for how residuals behave under a giant pull. There is one more verdict to carry home. The method worked. We named our tests in public before the answers arrived. We let Mars teach rotation and jet timing. We let perihelion set boundary conditions under stress. We let December write the ledger of change. We let Jupiter be the ruler. We measured what moved. We wrote down what did not. We allowed wonder to travel with patience, and we gave fear a seat that did not own the room. That discipline is a gift we can use again when the next traveler slides in from dark water with a new accent. If you want a final line that leaves room for awe without stealing from truth, try this. The universe sent us a stone that breathes a different recipe. We followed it with care. It taught us that natural can feel exotic when born in colder rooms. It hinted that worlds may borrow their hearts from neighbors. It did not yet confess to design. That is enough wonder for one visit, and enough work to keep us ready for the next.